Hall. Good morning, ladies and gentlemen. Welcome to the third day of GIAN workshop on advanced functional materials and green energy strategies. Ladies and gentlemen, I extend warm welcome once again to Professor Satish Patil sir. Due to technical issue, yesterday's last lecture has been rescheduled for today. I would like to extend a warm welcome to Professor Satish Patil sir, and I would like to express my gratitude for his cooperation. Despite all the disturbing events yesterday, he managed to keep all of us engaged with his interesting talk.
Hi. Check. Hello. Sorry.
Today's lecture was chaired by Professor D.M. Pore sir. I request D.M. Pore sir to take a charge and continue.
इथं का
म्हणजे तुमचा फेस
टोका इथून खालून ठीक नाही
म्हणजे ते काय खाली तुम्ही दिसणार नाही
हा
म्हणजे तिथं वगैरे असताना तुम्ही
ओके
तुमचा फेस वगैरे
ओके ऑलराइट ओके
म्हणजे लेफ्ट साइड
I kindly request Professor Satish Patil sir to commence the lecture.
या ओके थँक यू
सर बॅटरी
हा
बॅटरी
बॅटरी battery
बॅटरी
it's okay yeah so he wants me to come up so it's okay all right so all right very good morning. I hope you had fantastic evening. So yeah, I think we will just begin where we left yesterday. We were talking about generally batteries, so I will just quickly walk through those slides which I already flashed yesterday, and then we will start talking from there. So the more and more I go in advance in my presentation, I will be talking more on redox flow battery. So generally in a brief, again, just introduction to battery, I was trying to emphasize this slide more and more. Why do you need batteries? In general, what's the importance of the battery? And without battery, these things are going to be difficult, right? To store energy and supply when there is an intermittent power supply from the sunlight, so we need to have a very good storage. So this is, we can't hook up things like you just take solar cells and batteries. There has to be something called energy management. Okay, so don't think up like that. So if you're just thinking of hooking up a battery and interfacing solar cells, that doesn't work like that. All right, so you need some support from electrical engineering people. There is something called energy management cell, where they control interfacing these two and make sure that you have a sort of energy management. Suppose you are withdrawing a lot of power on this side, you again need energy management, right? You can't just empty the bottle, whatever you store in a bottle in a one shot. So it's important we just store energy and manage it. Energy much better. So this is slide which I already talked about it. Again, I will not spend much of a time. Why we need batteries. I essentially talked about there is again very rich history of innovation in battery. You see, batteries were invented where there was no people did not even do a neat experiment, but they could manage to stack these kind of electrodes in their garage, wherever there is a place. They did this beautiful work, and that's where we are all are beneficiary of these phenomenal scientists who did this extraordinary work in the area of battery research, and certainly we are advancing further and further, but there's a lot of work has been gone behind. Okay, so this is again more emphasizing they are indeed ubiquitous where they are. I was just spending some time yesterday here. You see that this is the electric scooter. Down the line, 10 years, at least your generation is going to see everybody is going to have electric scooter now. Perhaps cars are going to launch very soon. There are certain limitations in cars, and we certainly use today in here in just smaller devices, space shuttle, and these are mainly supercapacitors. Unfortunately, I don't have much of a time to spend on supercapacitor, which slightly the mechanism is going to be different, the storage mechanism. But however, you need a lot of power to launching rockets. For that, the devices has to be very powerful. So in that case, the supercap work much better there. So, okay, so, and then cell phone, I talked about it. Okay, so this is again very inspiring for chemists, right? So I think, I don't know how many of you know that. This is John Goodenough. He recently unfortunately passed away, but when he received the Nobel Prize, he was at the age of 97, 98, correct me if I'm wrong. But he started developing this lithium cobalt electrodes. So all the chemistry was done by him, and these are the three people they shared the Nobel Prize. So this is very recent. It was a very long due for battery research. People were anticipating Nobel Prize, and considering the benefits we have today for the energy research, they received the Nobel Prize in 2019. So it's a good idea to read. This is I find his entire scientific journey is very inspiring, where indeed he spent a lot of time in developing things, okay, and different places. So he also traveled across different continents and did a lot of very good, interesting work on especially today lithium battery. What we see is all thanks to these three people, where they have done some phenomenal work. Okay, so now figure of merit. So this is all, again, I'm more emphasizing on basics. What is a figure of merit for a battery research? Okay, when you do you set up a problem in your lab saying that I want to really develop a new electrode material, so for the sake of example. But what are the parameters when you are testing a battery in the lab? Okay, you build a coin cell or whatever it is. It is important we need to look at these parameters. First is energy density. So this is the quantity which is the engineers refer in watt-hour per kg, okay, but it represents the ratio of the energy available from battery to its weight. How much weight you have, a mass of a material you store on an electrode. Okay, it's very again important parameter, because you don't want to have a heavy mass on the electrode. Lighter is better, so energy density is important. So when you have a very light mass and store a lot of energy, that's a good electrode material. But it's not easy to do that, right? So how do you store energy? And then power density, the speed at which you discharge the battery, right? Certain applications require that. You remember, like many of you start a car engine, right? You need a sudden surge of a power, right? You see that how much fuel you need actually. So it's a sudden power, that's where the batteries don't discharge very fast. So currently people are trying to introduce batteries in a bigger vehicle, for example, in trucks or buses or in a car. Mainly the batteries concerned is power density. They don't release the power even to start the engine. So majority of the currently cars are indeed have supercap interface with the battery. So the initial surge when you start engine, wherever you need a very fast power, you use supercap and control the battery. In the sense, it's a safety zone for the battery, because if you suddenly discharge battery, the batteries go bad. So you don't want to really suddenly discharge batteries. So it's important, these two parameters, they go in tandem, but however, it's always there's a trade-off. When you have a high energy density, it's difficult to again get both parameters boost up higher and higher, because there's a trade-off here. So that's the reason people try to interface two different devices. They use supercap for certain applications. They use batteries for certain applications. So you can't discharge the battery with very fast rate. So there's something called C rate. I think some of you must be knowing it. So how do you discharge batteries? So this is important. And then, this is a sort of a ratio. And high energy and power density is the parameter we are all of us trying to push harder and harder, where we can find, as a chemist, we look at a new material, try to identify new materials, where how we can really push these parameters and make better and better batteries. So this is a good way to begin it and ask specific question, how I'm going to design an electrode which has a high energy density, okay? How I'm going to design electrode which has a high power density. So this is where most of the chemists play, right? A lot of paper people write, We identified a new material and it's working. Okay? But as a student community, don't really get into this completely doing very incremental kind of a research. You make it something, you charge, discharge, you find always energy density, power density. Okay, you need to really little bit think rationally how I'm going to really come out a new material. That's where Goodenough thought about it. If you look at his contribution, he literally thought very rationally about it. How I'm going to insert lithium, but however I'm going to really have a very high voltages, right? So that's very, very important to think over it. Don't get into most of the paper. It's flooded with literature. I get high energy density, people say. Somebody says I get a high power density. But what's the use at the end of the day? Right? It becomes one paper and next day people forget it. Right? So it is important again to understand and see that how are we going to really invent new materials on this basis. I'll give some example from our lab how we did it for flow battery. But it's again, we have to really think about how rationally how we can push these limits. Okay, so desirable characteristic, then it's important. As I mentioned, you need to have high energy density. It can be volumetric as well as gravimetric. High power density, both parameters, volumetric and gravimetric. Mechanical stability, this is where the engineers work about it, right? How rugged these batteries are. The mechanical stability is very, very important because majority of this interface between the electrolyte and electrode is determined by the interface stability. If your mechanical stability is poor or at the interface, then you won't get it. You eventually, over a period of time, the battery's stability is not as good as we anticipate. So that's the reason this is important. Flat discharge curve, high rate capability, fast recharge. That's where I think I was just giving example yesterday, because when you ran out of fuel, we immediately put fuel and now we are ready to go, right? We don't spend time on a gas station, like for example, couple of minutes, right? For putting your car in, you charge it and you run. So similarly, that kind of, if you want to replace, this entire, car, make it electric, you need that kind of fast charge, recharge capability. Otherwise, imagine that you go in the city, sometimes you get irritated, like how long we have to wait to fill the car. So nobody has the patience to wait for 2 hours to charge. So there's no way we can wait and say, okay, I'm going to charge batteries. So this is where you have to really need very fast charging. The soon after you start very fast, then you have those electrodes will start having issues. So stability becomes a problem. So this is a very open question. It's $1 million question. How are you going to really address these things? And people don't know yet. How are they going to address long life cycle life? Of course, temperature range. Batteries has to work on a tropical region. Suppose, for example, soldiers use it, very, very low temperature, right? For keeping them warm themselves. They don't have electricity, right? If they go to certain altitude of the, somewhere in Himalayas, they don't have it. So how they keep themselves warm? For that, if they're using batteries have to work. Sometimes these electrolytes gets completely frozen, right? If you have aqueous electrolyte. So in that case, you need to really figure it out the mechanism. It's good to test batteries across the different temperature range. Of course, we cannot. So wider the temperature range for the testing, the battery is better and better. So it's important you just measure not only at room temperature. So majority of the people don't put efforts there, saying that, okay, I do a room temperature measurement, I'm done with it. But don't do that. Again, go back and check, see that whether you can do a wide temperature range. Of course, cost is for any technology. Cost is a very strong argument. People will not buy it until unless you make it very cheap. Okay, if you want to replace something existing, you have to really give people better things, right? It's like a light example I keep giving it. If you really want to replace these lights with LEDs, then we have to really make it cheap. Otherwise, nobody is going to really buy these things, right? So that's the reason, cost and safety. Safety is very, very high. Something is very dangerous. For example, you need to have a very high safety. Aeroplane, right? You go up and your battery is giving trouble. You can imagine that. You are 37, nowadays they go 36, how much? Very, very high altitude they fly. and your Airbus is having a trouble, right? You can see the danger. It did happen to Boeing aircraft when they start implementing these lithium batteries. So safety is a major problem in this case. So we have to really concerned about what kind of material. So in batteries, majority of the time, these hydrogen and oxygen evolution reactions are, sort of complementary. They do happen when you just go with a broader and broader potential window. When you have aqueous electrolyte, you start dissociating water. That's where we have to really concern about it. There has to be a safety management in the battery. If you don't have a safety management, then you have a difficulty. So as a PhD student, you should really make always these bullet points in your notebook, okay? And put it down somewhere on your desk, ask these questions. What is you are trying to address here? Okay, that's why you should think about it, a research problem, and then identify at least one of the parameters in your PhD thesis, not everything, okay? So this is something we need to really look into it, okay? So this is now I will switch the gear a little bit. I will go to flow battery, as I mentioned. In this context, I will show our work also. So this is there are different kinds of battery. Perhaps I must be having the other one. Yeah, here, this is the Ragone plot. So this is the interesting thing. You see that? What I have plotted here, system power rating, module size versus the discharge time at rated power. Okay, when you start scaling up the system, you go from kilowatt to megawatt, and you see that what happened to your discharge power, discharge time at rated power. So this is what it is. Basically, you see that hydro, compressed gas, these are the bulk power management here. And for any grid support, at least you need a minimum 1 megawatt plant. For example, if you decide to do everything by renewable to your entire Kolhapur city, you need a plant in a capacity of this. You can't put a capacity of this smaller one if you want to supply electricity to bigger towns. So in that context, you have to build systems in large size. Soon after you build systems in larger size, you see that the speed at what happens to the power. So this is advanced lead acid battery. That's when you see all UPS, as I was giving example. This meets many criteria, lead acid battery. That's the reason it's very popular. And then lithium ion battery, they don't meet this criteria. So lithium ion battery for higher megawatt plant, people have not yet built it. People just use it in cell phone or charging, a laptop or something smaller, but not as good as lead acid battery. So in this context, flow batteries works very well. They are as good as lead acid battery. What's unique about flow battery? If you try to understand flow battery, so this is electrode here. You have sandwich, these are current collectors, and you have some, and then you store electrolyte in a separate reservoir. It's not part of integration. Lithium battery works, basically everything is stored here. Whereas in flow battery, you have this catholyte and anolyte stored outside. Okay, they're not part of that integration of the electrode. So when you start charging the battery here, you just circulate the electrolyte. That means you can really independently, enhance power density and energy density. They're not intertwined. Okay, so suppose if you really have very high power density device, you can play with this concentration of the electrolyte, or you can change the stack. You put multiple stacks. So I will show you how we did it in our lab. So this is something, a very nice example, we have it. So we could stack multiple electrodes, large number of electrodes. Then we have to do stack engineering here. You start putting more and more electrodes, you anticipate some resistance at the interface. So we have to be very careful about it, what we do at this interface. So the beauty of this battery is, this is very good for, storage. In a sense, when I say good for storage, for grid storage. Okay, so pay attention to my word. When I say grid storage, see these kind of a reservoir, I'm building a 1 megawatt plant somewhere outside the city. Okay, I have a solar plant, which is 1 megawatt, somewhere outside the town. Then I need a battery. For that purpose, I can use this battery. So it's just for the particular location. It's not for space application. It's not for the car application. So one has to choose the battery right for the right application. This is fantastic for grid storage. So here we can really independently play with the catholyte and reservoirs, anolyte, and then you can keep circulating. So this is a battery where it's a sort of emerging battery where people have, tested and, indeed looked at some of the very megawatt, plants, how this works, and it works very, very beautifully. So what is the advantage? Okay. Flexibility with power and energy, as I mentioned, I already described you initially the parameter, what is power and energy density. Safety, operate at room temperature, and a deep discharge. You remember how deeply discharge your cell phone. You see that, how deeply you discharge your cell phone. Okay, so if you start deeply discharging your batteries, for in case of lead acid, right, if you deeply discharge more than 85%, the batteries go bad. You have to keep minimum power to recharge it. So it's important to have a good battery which has a very, very deep discharge. Whereas in lithium, you can do deep discharge. Okay, so that's the difference between the batteries when you are saying, okay, this is a very important parameter, how deeply you discharge battery. But in case of flow battery, you can deeply discharge things. So I will continue talking about more on flow battery now. Okay, so this is types of flow battery. Then again, battery research is very, very broad. You just see different types of flow battery itself. You see it's all liquid phase. This is vanadium. People use it. Okay, they flow vanadium, hybrid. They both liquid and solid, and there's all solid phase. Let's not pay too much attention and make things a little bit complex here, but there are types of flow battery also. Let's focus mainly on what is flow battery here. Okay, so this is the main emphasis of the talk. Otherwise, I have to spend a lot of time describing each types of flow battery. What are their advantages? And that in the interest of time, I don't think so I can cover that much ground. So I'll emphasize more on other type of battery. So here is the problem. So what are the types of flow battery again? If you look at the flow battery in this case, okay, there are flow batteries which are essentially here based on, this is aqueous, all the electrolytes is aqueous here. You see that, but the potential window is very, very limited because you use aqueous system. Beyond this potential, if you go, you can, if you go more than 1.5 volt, you see those complementary reaction as I mentioned. Okay, hydrogen and oxygen evolution. So in case of aqueous battery, your potential is very limited. So limited temperature range, if you go, perhaps things will work at 0 degree, up to 100 degree, but if you use water as the electrolyte, you cannot go beyond 100 degree. Okay, so limited redox couple, then this window is very small, and it is demonstrated at pilot scale. People use a non-flammable aqueous solution. That's the beauty of this battery. Right? Safety, as I was mentioning, water doesn't catch a fire. So as a result, you have something in non-flammable aqueous solutions in a battery. But as an organic chemist, you start thinking about organic batteries now. Okay, suppose if you use organic batteries, these are all the redox couple, possible redox couple, the potential window is huge here. You can go from -2 to 2 volt. Very broad range because your electrolyte is not dissociating now. Soon after you go to the very broad range, in that case, non-aqueous electrolytes have wider electrochemically stable voltage window. So it can go up to 5 volt, but theoretically, which is 1, but we can at least build a battery up to 4 volt. So this is the beauty of making non-aqueous. But however, it comes with its own cost. So the major problem here in this one is the safety. This one, it's very, very safe battery, but if you use any organic solvent, anything organic you use it, you see that organic solvents are generally not safe, right? They catch fire or whatever you try to do with this one. Indeed, there is a issue of a safety, but you can change in solvent, acetonitrile, DMF, okay? Greater diversity means I can use whole bunch of a new electrolyte here. Anolyte, catholyte, as a chemist, you can go back and design in the lab and you can use whole bunch of electrolytes. Cost effectiveness is there. I'm not that sure what is the mean it, but this is something which we need to, it's a debatable. And then we have more redox couple. Here we have a very, very limited window. Okay, so we tested both the batteries in our lab. When I'm giving example, I will give example of how we tested this and what is our belief. what theory we believe which battery should go up front in terms of what is our experience and what that research taught us, saying that this and this how we did it actually. Okay, so I will give both the examples in the lab where we did aqueous, we also did non-aqueous. So just for the sake of understanding it, what is the major focus of our research, what is the direction we should take it by learning the lessons from these two batteries. So this is very clear right now, where you can use organic catholyte and electrolyte, whereas you can use the aqueous system. So this is very, very clear in saying that what is the major advantage and disadvantage of use organic versus aqueous one. Okay, so going forward, okay, this is very important electrochemical stability window when you are designing a material. Okay, for example, this is what your energy diagram with respect to vacuum. When you design a battery, we have to avoid these reactions, right? For example, when you do a redox chemistry on a electrode, you generate these electrons, right? So there, this material has a soon after reaction with water. So anything is bit of a hygroscopic electrolyte, then you have this again hydrogen evolution reactions, which is you don't want. So you have to play with the potential window of below minus 3.5. Your LUMO, actually, when I talked yesterday about HOMO-LUMO, you remember, right? So your LUMO region has to be below minus 3.5. You have to ensure that it lies there, because anything above this, you have a reaction, which you don't want to. That's undesirable reaction, right? And however, when you see this here, if your homos are here, you see the reactions with oxygen. You have also reactions with oxygen. As a result, you generate these hydroxy radical. So it's a very narrow potential window for you to design a electrolyte as a chemist. But we have to start somewhere, thinking about how I'm going to make a material which has these reactions sort of should not create a trouble when I'm running a battery. So this was the sort of window, potential window, we utilize it. If you just do a Google search, or what is the major challenge in redox flow battery? One of the major challenges is anolytes. Okay, I talked about catholytes and anolyte here. If I go back here, stability of anolytes is very, very challenging. Majority of the papers, people debate about it, how to design a material, organic material which has stability, higher stability. There are many catholytes are available, but however, anolytes are very limited. Very few people work across the globe to make it design new anolyte. So we picked up this problem first, addressing the question saying that, can we design anolyte? The way we started looking at this problem is, how are we going to really understand this one? What's the problem when we design anolyte in the lab? We come across this interesting idea of saying that these are the main reactions which are major culprit of damaging anolytes and catholytes. So we need to really address these issues. So how we did it actually. So I'll give you a quick one example. Perhaps we use this is a basic chemistry we used it. Okay, so we use something called donor acceptor structure. As I think organic chemist in the audience, they'll be very happy to see some chemical structures now here. So idea is very simple here. You use some acceptor here and donor, use pyridine, and then we sometime what we do is we make it this group as a nitrile. The idea is push the LUMO deeper and deeper, make it material which has a very high electron affinity, and push it this window, bring it back, bring it down the LUMO deeper and deeper and deeper. That's the idea first. So this is what we synthesize, let's say 4 molecules in the lab, and to test the idea of saying that how we are going to really make it. See the LUMO here, 3.1. Soon after you put a nitrile group, the LUMO goes below -4. Means the idea it is at least working. At prima facie, in the beginning itself, we see that this becomes very high electron affinity, just pushing the LUMO down and down. So this first example where we did the structural modifications and then they did the cyclic geometry. Okay, so this is a simple experiment everybody can do in the lab, where you see that and try to understand where are my sort of potential windows here. So you see that this is the current we applied, and you see this is with thiophene. We don't see much of a clear reduction peaks here. So this is the scale for common for all, and this is the current density. What we are saying is when you have a thiophene, we don't see much of a reversible current here. The magnet, it gets oxidized very well. But however, if you reverse it back, we don't see similar current. The CVs are not symmetrical. However, when you do a nitrile, we see a beautiful 2 electron process here. On a negative side, you see a 1 plus 2. These keto groups are getting reduced. Okay? As a result, this one, and here we are trying to stabilize these radicals when we introduce here, and we have a very nice, CV for thiophene as well as selenophene. Whereas pyridine shows interestingly one peak, but we can't, we are not able to reverse those symmetrical CV. So this is an important lesson, and this is the experiments. Many people forget to champion it. It's easy. It doesn't need much of a facility in the lab. Just you need a potentiostat. And you have to be very patiently do cyclical geometry. When my students really bring this kind of a curve, this took really long time for them to figure it out, what's going on here. But they are very patient, right? They keep coming back because you have to really play with what kind of current you apply, your electrode. You need to really pay attention. But this is a simple electrochemical experiment where you can champion it by practicing again and again and again. Don't never give up. Soon after you see the curve, try to understand it. What is the origin of this curve? Otherwise, you keep swapping something and you say, okay, here is a CV. So it's I see majority of the chemistry students, they don't reproduce good CVs. So that's a problem actually with the student community. So we need to really address these issues. So, but as we have to really motivate people saying that what we learn from a CV. Okay, so I have visited hundreds of cities across the India. Everybody has potentiostat. So nobody has saying that I don't have potentiostat, right? It's a very simple instrument. Everyone has it, but they don't utilize properly. So whatever we learning, people just give up immediately. So organic material CVs are again hard to reproduce. So you have to be really patient and try to understand. Rationally, you can conclude many things. I don't have to build battery with this material now, because it is not giving me any reduction peaks. So why should I waste my time going forward again? Of course, it can give me some charge discharge curve, then becomes one paper. Who cares, right? It has no value if you go on forward and then do it. So, however, we need to really think about it. I got very excited after seeing this CV. Then I said, okay, let's take it forward now, try to build a battery. Otherwise, there is no point. We discard these materials immediately from your list. We learn the lesson. These are negative results, very well described in the paper. If you read this paper, what we published, but we emphasize more on this one, taking it forward. What happened to these materials? So this is the way we went ahead and we built it. Actually, this is flow battery where we have used, we purchased from the shelf, from the catalog, some catholites, because our research was more emphasized on anolite. So we talked about this one and we just pumped these electrodes, and it's very easy to build the battery. But what we observed here, so this is different electrolyte again. So you have to use different electrolyte, which is the right good electrolyte. This is TBA-PF6, is the size of the ions, it's very, very important, sodium triplet or lithium TFSI. Okay, so we took different whole bunch of electrolyte and looked at the CV. Indeed, it plays a role. You see that here again, the choice of electrolyte is very important in battery research. One has to really pay attention what electrolyte suits to your anolytes and catholites. So here the idea is we use TBA-PF6. You see that is beautiful CVs here, very symmetrical, and we go with large number of cycles. It's very stable. Whereas when you do a sodium triplet, we don't see that. Okay, so we again explain why we don't see that, and lithium TFSI, we see this kind of a CV. So this is multiple curves here. We ran you see there's a difference in here, peak positions. Here you don't even see that. That's so beautifully at same place you are doing redox reactions, multiple cycles, and this molecule. Okay, whereas here we see a little bit of a difference. Here we don't see much of a current here. So it means there is no proper electrochemical reactions between these electrolytes. So it's again very important lesson. Everything from CV so far. Going forward, choice of electrolyte, we build the battery. Then we put both initial blow and then TBA this one, and then we build a battery. Theoretically, we calculated how much the potential window from the peak positions, how much we get it. We get it 1.4 volt battery. It's not a very sort of a battery where we aimed, at least when we wrote proposal, we said to DST we will make it 4-volt battery, okay, by using organic electrolyte. That's still a challenge in front of us. But we indeed started somewhere looking at how we can identify electrolytes. So we could manage to go to up to 1.4 volt. This is simple battery. Don't be afraid of it. Anybody can build battery, right? So just start somewhere and things get, it's easy. You know, at least I found it, there's nothing like rocket science here. Why can't build the battery? We went ahead and built the battery, we start charging, discharging. So this is a crowded slide, lot of data here, but we see a different plateau here. You see that here. We went to after up to 100 cycle. So this is not some of the steps what we are seeing. So we did not do a very good battery here. In a sense, you see the cycle number. It is indeed, you have a capacity, it goes down. And similarly here, cycle number, the efficiency also goes down, Coulombic efficiency as well as this voltage efficiency. It's not a very good ideal battery, but here energy efficiency and Coulombic efficiency, here we find it much, much better data. But now we started understanding where things went wrong. But we are the first one, we are saying in the paper, in essentially we built a stable analyte. Something is wrong with this one, right? It is somewhere the battery did not give its anticipated results. So we went back and did more spectroscopy. So this I will skip it. We did a lot of this potential stat charge discharge cycling. So this is more and more. You see that here, as we progress in cycle number, it discharges very, very fast. Something is totally wrong with with the way we are doing it. Then we went and we did spectroscopic tool now. So this is sort of understanding where things went wrong. So we did every cycle, we collected some amount of electrolyte and we monitored with UV visible spectroscopy. In a sense, unicell blue in neutral has these two beautiful absorption peak at 644 nanometer and 597 nanometer. Very nice vibronic peak. But soon after you start charging, this is a 5 hours, 1 day. You see it's a sort of start degrading the material. So unicell blue has some issue. We did also in situ NMR to understand where the site of degradation. Similarly, this is the DBB. This is again a simple organic material. You see that here also as a function of time, it just completely degrades. And similarly with the nitrile material, which we developed in our lab as a analyte, we see here up to 2 days, there's not much of a change. So it says the analyte is stable, whereas the catholites, whatever we use commercially available, they somehow, did not survive. Okay. So this is again an interesting experiment where, again, thanks to student, they did very, very carefully as a function of time. He collected the sample and looked at then we concluded in a paper by saying that what are the possible degradation pathways for the battery. So this is just an important lesson we learned from this project, saying that it's not only analyte, indeed some of the catholites also undergo degradation. So if you really want to make a good battery, we have to build both catholyte and anolyte and improve the stability overall in the future. This is the lesson we learned. And this is one conclusion. Before I switch to aqueous, how much time I have now? How I'm doing with time? Another 20 minutes? Okay, that's fine. So what is the conclusion made? A new class of organic material we introduced. A proof of concept. That's what we built actually, a flow cell, right? So that's where we did, and then we looked at what is the major problem with major issues with the battery. We use UV visible absorption spectroscopy as a tool to understand that. So this doesn't require very, again, high infrastructure. Basic instrument, it leads to this problem. Okay, so I think I did not give a reference somewhere, but I think this paper has published in Chemistry European Journal, somewhere it published, but you can look back actually, see where we published this whole data. So now let's look at aqueous now. We started working on, again, a very interesting project. We took this soluble lead redox flow battery. So here the idea is simple. The electrolyte is aqueous. Okay, we don't take it non-aqueous electrolyte. And the idea is here we need a lead methensulfonic acid here. Okay, so this is electrolyte. The beauty of this battery is we don't need two different anolytes and catholyte reservoir. in a single reservoir, you can store it and you can pass through here this electrode and you can build a battery. So there is a simplicity. It's like a lead acid battery. It in fact actually functions like a lead acid battery. If you look at what are the possible reactions at anode and cathode, generally you can go to cell voltages up to 1.62. You can push a little bit beyond some kinetic stability. And this is the sort of a battery. The first problem we encountered is, okay, so what are the advantage? If you ask me the question why I believe it, single electrolyte, no membrane, low cost active materials, you can make it kilogram. We make 10 kilo, literally 10 kilo in the lab, okay, whenever we build this battery. And widely abundant material, and then there are challenges. Soon after we see that, we don't have to even do FESEM. We see a huge, massive dendrites growth on the surface of the electrode. You see that it is just falling it off here. Okay, this is just a natural naked eye observation, where we clearly see there is a lot of sludge is forming. Okay, then now we started understanding this and address the question. So we first looked at these three surfactants. Okay, so this is known in the literature where we have additives. You can add additives to prevent the dendrite growth. Surfactant traditionally do that. Okay, they sort of somehow they freeze the growth of this dendrite. This is not good for the battery. You don't want that on your electrode surface. So eventually, if you use these surfactants, sodium lignosulfate or hexatrimethylammonium pertolene sulfate or triton is a common name for this chemical, where there are some non-ionic surfactant, cationic and anionic surfactant. We need to test that now. In the battery, how are we really going to really address this? So we can prevent dendrite formation. These are this one, and then we can also add additives on both sides. Okay, and then see what's mean. So you can't add these additives in large quantity. You have to add a very small, tiny in quantity and check it, test the idea whether it works or not. So we went ahead and built it. This is a lab. Okay, we started a cell building in the lab. Okay, so you see that our tank is simple round bottom flask. Okay, so simply round bottom flask, we built a battery, we started pushing up electrolyte and test the idea here. There's a very excellent PhD student who did this work, phenomenal work. So this is the one which he looked at very carefully. He started adding these three and started feeding us with the data, saying that what happens? Do I see a growth on the electrode or not? So first, okay, FESEM now. He looked at the data again carefully. What happens to anode and cathode? Anode and cathode and anode and cathode. You see that this is his observation. Thick deposition both in SLS alone, but SLS NF binary systems become relatively smooth. That's his first observation. Okay, by adding here sodium fluoride in a electrolyte. Surface becomes more porous, okay, here after adding sodium fluoride. So that's the first observation by looking at FESEM. This one he add different surfaces. Surface retains non-uniform nature. It's very non-uniform here, from here to here, okay, with microflakes. However, cathode upon adding solution of this one, it forms a uniform and porous deposit of lead oxide. So this is very, very important observation. Okay, so one has to really carefully look at what is happening here. And this one here, surface shows smooth deposition of lead along with lateral direction. You see, these are the lateral directions. Okay, and cathode we see a binary systems. So we again started thinking about it. Which is the right surfactant we have to use here now? By just looking at this data, see that what is the right surfactant? How we can choose the right surfactants to avoid those dendrite growth. We move forward and look at cycle life of this one. So here is the interesting, this is again very crowded. You see the Coulombic efficiency it retains. Okay, initially it takes some cycles to reach to close to 100, but you see that SLS with sodium fluoride, we don't even see this color. So it's a very clear observation that up to 70 to 80 cycle, we can retain it. All these data where we have pristine electrolyte, we don't reach Coulombic efficiency up to this one because of the dendrite growth on the surface of the electrode. When you add these, additives, we do see that. And some additives, we see a drop in Coulombic efficiency. So something is really working very well. And if you try to correlate results with back, you see that what is the best, electrode we have seen, sodium fluoride indeed work among three. Okay, so we went ahead and then did Okay, some of the ideas, we scaled up the battery by using this sodium fluoride. So there was no prior art available when we started working on it. Okay, so there was a group in UK, they had some data, one PhD thesis, but how are we going to stack it now? Okay, stack engineering was very, very important for us. Without, like, this is no prior art. We looked at the literature, we were the sort of first one to do in the literature. How are we going to really do a stack engineering? So we went ahead and start building these stacks. So this is more like a, sort of understanding where are the shunt, because as I mentioned, you start putting, I don't have a board here because you start putting multiple stacks, many stacks. You start, every stack comes up with some resistance okay. So it was, but however, when we did this stack engineering, we try to understand the resistance. What are the leakage current we find this one? So we test battery for 5 months, 6 months and see where are the leakage current. What's the best stack engineering we can do it? So this is more to understand the shunt currents, and then we build the circuits and see that where are the main short circuit currents are. So we took it forward, and what are the manifold? How are you going to flow it? Whether we need internal manifold or external manifold. So this is a lot of flow designs. We have to talk with a lot of mechanical engineers and see that how we are going to really build this stack here. Total stack voltage, this is shunt current, electrolyte conductivity, design of electrolyte feeding system. So whether we do this or we do this, how are we going to flow a liquid in a stack? So that's basically the idea. And then we sort of built this battery. So this is currently, okay. We started, I think perhaps Suman has a much better picture here, maybe going ahead. No, okay, he has a picture here. I'll come back again to those slides. So as a part of his PhD studies, he started his PhD in 2016. So he's a postdoc in somewhere in Israel. So you see that this is his first observation. He went up to 1300 cycle and then came back to us saying that we can't build this one. But this was our mandate. Actually, as a part of a project, we are supposed to take battery up to 8 cell stack. Now we are taking to 1 kilo stack. So we are building a better and better battery. But this is the way we started demonstrating things to a funding agency, saying that we can build things from, just from the scratch. Okay, so we take everything we learn. There's a lot of chemistry here we learn, and then we start doing stack here. So now currently we stand here. We demonstrated a fully functional 8 cell, soluble lead redox flow battery with this capacity. We had 500 centimeter. This is everything in the lab again. It's a massive one. If I don't have video here, or perhaps I have video how student built it, but I don't have video here, unfortunately, but they built it together. So they make it this massive stack in the lab. So go back and little bit spend some time about what we learned here. So this is all about shunt current. This is more like, okay, so this is where we see the charge discharge cycles, very stable as a function of a time. We see with internal manifold, whereas in a external manifold, we see a different profiles here. Okay, so stack with external manifold has least effect on polarizing middle cells. So that's a lesson we learned. And then we went ahead and test the 8 cell stack. 8 cell stack has beautiful performance, you see here, as a function of a time. It's a very stable stack and it works very, very well. And this is what our energy and input and output, and this is what total energy efficiency of this cell. Okay, so this is, I'll conclude. I hope I'm on time. You see that if what we built here, okay, now non-aqueous flow battery, we are still hunting for those best catholyte and anolyte, but we built a 8 cell stack with 500 centimeters square active area. And there is also, we make series and parallel combination. The battery is developed and we demonstrated 12 volt, 250 watt hour battery with a maximum power output of 232 watt. And the stack showed stable cycling behavior. So that's our conclusion. So this is a fantastic grad students who worked on this project. So Suman started all this beaker chemistry. Okay, he began his PhD. Shikha did this anolyte work. She was an organic chemist by training. So she was just trying to understand this catholyte and anolyte business. And this is the new student now took over from him, trying to take things to 1 kilowatt. So his challenge is much bigger now. So looking at, and then this work is done with fantastic people in the department, in our own department. Professor Shukla is retired, superannuated. He's sort of in advisory role. And there's a new colleague of mine. He just joined us from Stanford, Professor Nagafani Atikuri. He's an assistant professor in the department. And we got funding from all these funding agencies, including as a global challenge research fund in UK. Okay. With this, I'll thank you very much. I'll be happy to. Okay, questions, please. Anyone? Yes, please.
Explain the role of pump and reservoir, exactly why it is used.
Pump and reservoir, where? Okay.
And how does it affect the battery performance?
Should I explain you what is this initially when I showed a picture of a pump and reservoir?
So any is fine.
Here?
Yes.
Okay. So you see that these catholites and anolytes, the reservoir means a storage. You can have a beaker, you can have a tank, anything is a reservoir. Okay. So what we do is we circulate here through the electrode. Okay, and redox reaction happens at this electrode, and we collect it back again. So it is just constantly circulating anolyte and catholyte, where we do charge discharge at this place, and we get back. So this is the reservoir. Reservoir is a constant source of electrolyte.
So in terms of performance, like you have to maintain the flow rate and those
Of
things.
course, that's a very important question. We have to play with viscosity. Okay, so flow design. Okay, we have a faculty in IISc who is a mechanical engineer. Their work is they try to understand the flow rate. Okay, so how they in fact are not mentioned here, but they helped us to design these electrodes, external manifold versus internal manifold. Okay, we came up with that design by talking with them. They sort of helped us to saying that, okay, this is a good design for your battery and this is the flow rate. So when you are designing this one, you can't just mix concentration as you desire. You have to really play with the viscosity of the liquid. Flow rate has to be constant. Otherwise, our output in the battery will not be constant. It will fluctuate with the current. Yeah, so we have to play with the flow rate very, very carefully. Otherwise, you are certainly in trouble. Yeah.
So second question what I had was regarding the choice of electrolyte. I mean that you decide from literature or like how
So
to decide?
choice of electrolyte is specially for the flow battery, for the catholyte anolyte, as I explained this plot here, right? This is something a stability region, where we test our ideas of saying how stable is the electrolyte. Electrochemical stability when it undergoes the redox reaction. Okay, where is the homolumos should be when you are doing organic material. All right, so based on that, we sort of try to avoid these reactions where we have a side reactions and undergoes hydrogen evolution. So we sort of look into, based on, there's a rationale behind it, how we design the electrolyte. Yeah.
So then third question what I had was like in some reports they have like Coulombic efficiency, it goes above 100%. So is there any reason behind that?
I don't think so. Those are, you should not read that results like that. If you see the Coulombic efficiency, whatever we have shown here. So the Coulombic efficiency we have shown most of the flow battery work which we are doing it here. Coulombic efficiencies cannot be more than 100%. So you see the Coulombic efficiency here, this plot here. You see those fluctuations, of course, those dip fluctuations, you see there are a lot of, some disturbance in the current, the way it is, but the Coulombic efficiency cannot go, more than 100%.
Thank you, sir.
Yeah.
Can we use multi-junction semiconductor in solar cell?
Multi-junctional. Yes, that's tandem solar cells. I talked about yesterday about light management. You do not have a single semiconductor which covers the entire solar spectrum. Right? What we get from the sunlight is a distribution of a wavelength. You get light in UV, visible, near air path. If you build a single junction solar cells, You cannot absorb all the light. And then naturally you have a loss mechanism. So if you build tandem, we can have semiconductors stacked one after other, which absorbs, let's say, a red part of the spectrum, blue part of the spectrum. So those are tandem cells. People built it, but these cells are complex. Again, you have to play with interface engineering when you start, stacking one above other. So the single junction solar cells are very simple. So there's a cost involved. So you have to pay cost. There's a trade-off there. Tandem cells, it's not necessarily follow Shockley quasar. They go beyond Shockley quasar. Whereas single junction, it remains efficiency. So people have demonstrated very high efficiency tandem cells. Yeah.
Okay. Thank you.
Yeah.
Sir, I have to ask about the dendrite formation. Suppose in electrochemical studies, in concern with the supercapacitor and batteries, dendrite formation is considered as one of the constant. But in the same electrochemical application for the water splitting or the solar cell, dendrite formations are better.
Yes.
What exactly it makes difference?
So here the dendrite formation has, see, for example, on the surface when you have dendrite formation, the electrochemical reactions is not at all uniform on the surface. Okay, so in battery you have a sort of, you insert the ions in, out here. So for this kind of a redox reactions, you need a very smooth surface in battery. Okay, so photocatalysis, perhaps Prashant can address that, he just came, but photocatalysis I'm not a really expert, I have not done much of a work, but how the dendrite help actually in photocatalysis. At least in a battery I can tell you what's the main problem in the battery. Any kind of a redox here systems, for example, you have electrolyte next to these electrodes, right? So you don't have wetting of the electrode itself is not completely non-uniform when you have such a growth on the surface. So you have to really avoid those. Otherwise, insertion of ions, smooth surface versus this one, you can imagine, right? So that's where it hampers the stability. You don't get the output current as same as this one. So we have to avoid dendrite growth here. Yeah, at least in the case of battery. Yeah. Yes, please. Okay, I think she has first raised the hand. Okay, I think it should go to her. Please, just stand up and then, yeah. What do you want to know about platinum disc? Is there anything any specific? Platinum disc has been commonly used as an electrode material. It's a sort of, yeah. So it's anything specific you want to know, or you just why platinum is the question? Why platinum is commonly used? It's stable in those electrolyte conditions. For running series, platinum electrodes are preferred. Yeah. Okay, so in flow battery, whatever we were talking about it, this is a, when we build this kind of a major stack, very, high capacity stack, when you build it, certainly we have to think about, these electrodes mechanical stability. Because sometime if there is a minor bend or anything kink in electrode in such a big battery, you start seeing the undesirable reactions. So, and you also have, as I mentioned here, when you build this stack, right? When you build this stack, each stack has its own resistance, right? So stack engineering has to be done carefully because your overall energy and power density depends upon how many stacks you have in a battery. So in that case, what happens here is basically, if there is some sort of a bend or anything happens to these electrode, the mechanical stability, I made my argument in that context. If electrode is not mechanically stable, then in that case, you don't have a stable performance of the battery as a function of time. Okay, when you keep exposing these electrodes, these graphite electrodes to the aqueous electrolyte, there is naturally they start also swelling, right? You do not want to have such swelling of an electrode. That's also a mechanical stability. In that case, you don't see a correct output. We have not done in this case temperature studies, but one has to do temperature studies. I agree with you. You can maintain in the atmosphere. Yes, we can test it that. Last question. Yes. Somebody, no, she has it. Oh, sorry. Okay. Yeah, please. Hi.
On the battery, but I have some more question related to it. What is the lifetime of the battery? It's like market some vehicles have battery.
That's. I think if I answer you in one statement, it will be misleading. But it depends upon kind of battery.
Okay.
See, lithium battery, lead acid battery, which battery you are talking about. It depends upon application. In cell phone, you use lithium battery, whereas for UPS, we use lead acid battery. We don't use lithium batteries. So the lifetime of battery depends upon how much current you are withdrawing and the nature of the battery. Okay. So I don't have a clear answer saying that this is the stability for this battery. I think otherwise I will be misleading. I hope Prashant can comment on that. But perhaps what I'm saying. Yeah. Yeah. Yes.
Means
Yeah. Yes. Yeah. Yes. Yes. So how many cycles you run on the battery? It depends upon that also. So there are multiple parameters talking about stability of the battery. Suppose you charge very fast, then also you damage the battery.
Yes.
Okay. In that case, I was giving an example of this sudden jerk when you start engine of the car.
Yes.
That's a very fast discharge. You need a lot of power for that, right? So that's the reason people in electric car, they use supercapacitor interface with the battery, because it gives a safety zone for a battery, just to give a sudden jerk. You don't want to start your engine with lithium battery, for example, right? Because it's a very sudden jerk.
and once it's whole damaged, what about the reusability? Means is bio-waste? No?
See, basically recyclability is an important question. People don't know yet. The purity of this lithium, for example, has to be very, very poor when you build batteries. Okay, when you build and you destroy it and try to recover again, it's hard to get the quality of the lithium where you started with. So there are a lot of people are working in India, especially. There's a huge demand of recycling batteries.
Because it creates more waste. No?
Waste. It is create a waste,
Yes.
and that's a big problem. Hopefully, our next generation don't have to work up handling waste, but that's also an energy problem. I think it's important to think in that direction, saying that whether it's a recycle or not. Actually, I did supposed to have one slide on that, but I don't know whether I put this one or not. At least in this presentation, no. I think somewhere I had some slide. Okay, I don't have. I forgot to put this slide. But battery chemistry we was talking about. I think no, I don't have that slide. But there is a question. I asked that question. Yes. Yeah.
Thank you.
Hello, sir. Sir, in this flow ion batteries, we are actually working on the electric double layer, which is non-stationary. So electrolyte is in motion. So is there a contribution of streaming current in discharging process?
Yes, that's important, because it's not stationary. It's that's the reason the flow rate is important. How you flow. You have to study the output current as a function of flow rate. And then you have to arrive to the conclusion saying that if I was talking about adding additives to avoid the dendrite growth, but then it will change the viscosity.
Finally,
as well as the flow rate.
If you measure the electronic mobility of the organic material, we can also control the flow rate.
Yes, it has to be optimized. Yeah. Yes. Yeah, please. How to calculate, or what is the question?
Solar cell and concentration of sunlight on efficiency of solar cell.
Yeah, it does, because see the number of photons which are shining on the surface, right? You see what happens when you test in the lab. We do a tiny centimeter square device, pixels, right? When you enlarge the area, right? It's because what been installed on the sunroof is a module, massive module, connected with the different, So when you are increasing the area, the efficiency drops because of the resistance. Okay, so it is important. And also sunlight. When you're doing a measurement in the lab, what we ensure that we shine one sun. Okay, because we create the environment in the laboratory by having a solar simulator saying that we always shining one sun. So don't shine the light by taking them very close. Your efficiencies are going to be very different. So we have to be careful about it. We are getting one sunlight on your device. If you shine more and more, there are solar simulator people give 1.5. Okay, there is something called, okay, I can teach that in my course, I teach it, but it's called air mass. Okay, you have to really make a reference cell saying that this is one sun. And then based on that, you have to define the area and define the intensity of photon shining on the surface. And then you calculate the efficiency. Yeah. Yes, please. Yes. Redox flow battery also has issues with the power density. Majority of the battery mechanism itself is you insert the ion and do the redox chemistry. Whereas in supercap, you do at the interface. It's a double layer. So you can fast discharge, you can very get high power density in supercap because the storage mechanism is very different in supercap versus battery. So that's the reason supercaps are fantastic power devices, whereas they are poor energy devices because double layer cannot store very high energy. So all the batteries have issues with the power density, whereas energy densities are fantastic. Okay, that's true with the redox flow batteries. Yes.
Redox flow battery having the low thermostat or it's circulating the electrolyte. So like RD, it controls the diffusion controlled current.
Yes.
That's why it having that much of efficiency of that particular battery or?
No, it's not a diffusion of a current because that RD is an experiment where the way you do this rotating disc electrode in the lab and trying to understand, stability, for example. So whereas in flow battery, the main source is this anolyte and catholyte. So concentration of these anolyte and catholyte determines your energy and power density. And of course the flow rate. Flow rate is important. Okay. So yes, it's you can make that statement. Perhaps it is controlled by diffusion current. That's true. But these two are independent experiment. Okay, RD there's some purpose to understand. Whereas this one, just build a battery. When you build a battery, one has to really pay attention to this concentration of these electrolytes. In addition to that, what is the flow rate? Yeah. So, but it is both are controlled by diffusion current. That's correct. Yes. Yes, please. Yeah. Really? But we can use it both. That's fine. Yeah.
But our material we use as a working electrode, right?
No, you can use as a working electrode as a platinum also for running CV. Yeah, but see, this electrode choices depend upon what material you have. You need not be necessarily have to use platinum all the time. Okay, depends upon. You can use the reference electrode differently. Silver chloride. There are many like mercury sulfate. There are many electrolyte, electrodes you can make it. So your choice of electrode, it depends upon what is the stability of your electrolyte. Okay, what solvent you are using it. So it depends upon that. Platinum disc is very commonly used for running CV. It's more stable electrode compared to other this one. Yeah.
To our question, like what exactly I doubt, platinum as a counter electrode, now studies are showing that in terms of ORR reactions and some other electrochemical reactions, the platinum molecules, they get deposited and it can affect the performance.
If
so
you
it's better.
continuously use again and again, yes.
So in that case, then how you justify the performance what you got was not of platinum and that of it?
No, that we cross-check it. See, the platinum surface, whatever we have, see the drop in efficiency is not because of the platinum. Electrode has been corroded. That's we can always test stability of the platinum electrode. Okay, but the moment you see the drop in efficiency because there are other complementary experiment we are doing it. Right? So for example, in a non-aqueous flow battery, I showed those UV visible experiment. The electrolyte is clearly degrading there. So those are complementary experiment you can ensure. And again, you can run a reference electrode, you can test it parallelly. seeing that whether it is giving the exact potential or not. Okay, independently by taking out, not necessarily in the same condition. So if your electrolyte and your electrode is good, then you can go back again. It can be tested. I think battery research seems to be very popular here. I think everybody should talk about battery groups like that. There are a lot of more.
So dear delegates, if you have more questions, personally I write email to sir. Because of time constraint, we are ending this session. So may I request Professor Pore sir, please felicitate. Okay,
You
Satish
don't
Patil,
have
sir.
to felicitate me. It's okay.
Yeah, it's our duty, sir.
Okay, all right.
It's our regular practice.
Yes.
Good morning to all. Professor Nitin Patil, Satish Patil accepted our invitation and from his busy schedule, he came here, delivered fantastic lectures on organic solar cells as well as redox flow batteries. So, on behalf of all participants of this GIAN program and Shivaji University, Kolhapur, I offer my sincere thanks to you, sir. Thank you.
As a token of our love. Thank you. It's fine. Thank you. Okay. Thank you very much. Thanks. Thank you.
Thank you, sir, for 2 interesting lectures. We are privileged to have you. Ladies and gentlemen, please give him a big hand. Once again, now I would like to welcome Professor P.V. Kamath, sir. We are all excited for upcoming lectures after yesterday interesting lecture on AI tool and PhD and beyond. Without any further delay, I kindly request Professor P.V. Kamath, sir, to commence the lecture.
I skipped that next lecture. There is to be. Let's go to the schedule. I will give this one tomorrow, but we'll go with the graphing.
Graphing now.
Yeah.
Now it's working. We have changed the camera.
See, I told you the cable. Because it was a problem with every computer, right?
Yes.
Okay, you have been having lot of different topics, right? First, I give you nanomaterials, then on properties of the materials, how to characterize them, then also liquid junction solar cells. You heard 2 excellent talks on organic solar cells, batteries. As you can see, at one end, there are wide variety of materials that have come up in the last 20, 30 years, and people are trying to get it, and how to use them. And one of these materials is 2D material. 2D is 2-dimensional, okay? Think about a book, and it's made up of pages, right? So you pull out one of the pages, that becomes one of the 2D sheet. If you have a graphite, and graphite is like a block, it's made up of a lot of sheets. And now the thing is, how do you take out the sheets? So that was a lot of effort went in, and now people are studying the properties because now you have a large surface area. Same thing happens in the batteries. They make use of this material because you want to intercalate lithium ions inside those things. So you need to increase the area. So in this talk, I will be talking about graphene-based hybrid materials. There was a talk scheduled from 10 o'clock on perovskite solar cells. That I will talk tomorrow morning, okay? So that we can maintain the rest of the schedule as it is. Okay, so now we'll get to the graphene thing. And there have been a lot of studies. So this is the campus of University of Notre Dame where I work. This is a global graphene market. The graphene word has become very popular after it got Nobel Prize by Andre Geim and Norusko. They got the prize, and so there are various forms which is available. One is called graphene oxide. That's most of us use, right? You oxidize graphite and get graphene oxide. Graphene nanoplatelets, few layer graphenes, monolayer, bilayer. So there are various different ones. And the real graphene people grow is bringing carbon source like methane and on a catalyst surface at a higher temperature. So you decompose and they form this network of graphene. And the problem is now you have to take that sheet out, and all the good properties goes with the one layer graphene. The moment it sits on a surface, it's interacting with the surface. It's no more the graphene property. So this has been a big problem to explore in electronic material, because either you have to have multiple graphene layers, or how do you hang this one layer of graphene? So this has been a big problem that's going on. But people have found out a lot of other applications. It doesn't matter, multiple layers. Automotive, because it's a conducting surface. You can have, it doesn't matter, you have one layer or two layer. If it is conducting, they can use it. Aerospace, pharmaceuticals, energy, coatings, electronics, chemical. So as a result, it also shows you the share. The automotive is probably the highest one that is being used, okay? So again, they have a lot of, again, there is a link here, you can check more on this market. A lot of people do techno-economic analysis, or what is the future for this product, right? So they want to know. So this is, again, another site from the graphene market. Graphene market revenues to cross something like 1.2 billion by 2030. So it's a huge market people are making. Again, how it is growing by 2020, you can see right from the chart. And again, they're saying the same thing where it is being used, and this is. So this area is going to pick up quite a bit, these materials. Where you use it, how you use it is a different story, right? That's what we are interested in, whether it's supercapacitors or batteries or some kind of a energy application. So everybody is exploring these materials. Okay, so you might have known this slide. Again, Geim and Noslow, they got this Nobel Prize for this. So they said that this is a graphene sheet. That's the mother of all carbon nanomaterials. So again, you can think about forming C60 with these ones, or carbon nanotube just wrap around. So again, sort of it becomes a basis where you have this aromatic ring put together in a two-dimensional way. The simplest one is, say, think about benzene, naphthalene, right? Anthracene, pyrene. So it is an extended this aromatic network that gives you that look of graphene. So that's why it's becoming very interesting. Okay, so let's do how people synthesize. Probably most of you know, but this is just for people who want to know more. One of them was, the first one they did was peel off from a scotch tape. You can take a graphite block and just put a scotch tape, and when you peel it off, the one layer that comes in, those are your graphene sheets. Okay? It's a nature made it, so you can take it. That's what I'm saying. It's like a book. When you have a book, you take out one page. So that's what it is. And the other way is this chemical vapor deposition method. This is the most cleanest way to make graphene sheet. And people have industrial processes. They use nickel or copper catalyst on the surface, and then they bring hydrogen and methane and reduce to form carbon in this one. So again, you can see here, these are each sheets they formed in this one. The third one is solution phase production of graphene with controlled thickness via density differentiation. Again, people tried it. If you sort of a mixture of all these different sheets, you put some kind of a surfactant to wrap it around, and then you centrifuge it. And this is called density gradient because it sort of separates out based on its weight. So if there is a 1 layer, 2 layer, they will go on the top. So here is 10 layers, and the larger ones stack up here. So this is the Hersem, Mark Hersem at Northwestern developed this early on, and he also had a company for this one and this one. So basically you put the surfactant, sonicate, and then you get these multiple different layers, and then you separate it out. Okay, that is the third method. What is the fourth one? Fourth one is by chemical exfoliation. Okay, so the chemical exfoliation is you try to force in either surfactant. That in the previous one it was like a forcing some surfactants in to separate out. Here what you do is actually oxidation. It's interesting that this paper was published in 1958. Not much attention was given, right? So because of this graphene thing, people just explored this. And so basically you put every known oxidizing agent, right? Sodium nitrate, sulfuric acid, permanganate, and just boil it for several hours, okay? So what happens is these bonds break and sort of carboxylic acid sort of goes on the edges. There are some epoxides on the things coming up. So again, there are variations exist in this one. So again, you can see here, this was done even in 1898. So it is not something new when you make a graphene oxide. It has been known. It is just you are exploring some new properties. And one thing is, when you make this graphene oxide and you make a suspension, it looks brown color, okay? And you know carbon is black. So very interestingly, you can, if you reduce it, just put some electrons. It could be anything. You can shine with a UV light. You can add some borohydride, or you can add any electron source. We added TiO2, right, and shine light. The TiO2 semiconductor can give electrons, and this powder will turn black. So that's the color change. People also have this, they take, if you have a pure graphite, you get this one peak. It's all carbon, right? So when you do this XRD, you get this one peak. Whereas when you make graphene oxide, you destroy that one. This is a aberration corrected micrograph. That's how a pure graphene would look like. But if you do oxidize, you can see there are a lot of holes because these are not graphene anymore. You can see here these pockets where these functional groups got attached because you're oxidizing this carbon-carbon bond and getting this vapor. But when you reduce it, you restore most of it back to, but still you have these functional groups not completely reduced. So this is again done way back. Okay, so what makes graphene oxide so unique for energy conversion, right? So we want to use it for energy conversion. So one is you can attach and modify semiconductors, metals, or some kind of a sensitizing dyes, in this case porphyrins. And the application include catalysis, making hydrogen maybe, solar cells, and batteries and capacitors. So that's where it is mostly been people studied in a variety of way. So this is how we started in our thing was we wanted to use graphene oxide and stabilize the metal particles. So we just added, this is a gold solution, and if you don't have graphene oxide, if you reduce it with sodium borohydride, you get an aggregated particle. But if you have a graphene oxide, you get a nice wine color solution, and yeah, you can see here the particles you can generate. We also put TiO2. This is one of the first paper with graphene oxide and TiO2. Okay, so we were lucky enough. This was done by an undergrad, was working, and we said, okay, let's try what happens. And when you do it and we shine the light, sure enough, this turned to be reduced form. So that's how we could publish it and then followed it up. And you can see here how it looks. And these are sheets when you spin coat it, and see how they stack up differently, and because the particles separate them, each sheets. So just giving you how you can make these hybrid materials. Again, we can see that they do interact with the semiconductor. If you remember in my previous talk, I showed you the semiconductor's luminescence, right? There is a fluorescence that comes in from this cadmium selenide. But if you add an electron acceptor, you can transfer this electron. That means this emission goes down. And that's what you see. If you take a cadmium selenide and this graphene oxide or reduced graphene oxide, they quench the emission. The graphene oxide quenches more because it has a more electron withdrawing capacity. And you can also measure the lifetime with how fast they inject electrons. So this was again done later on. Another thing, interesting property of this graphene oxide is they can store electrons, literally store electrons, okay? But that's why they are used in capacitors, ion channeling properties, electrocatalytic properties. So this electron storage property, just somehow electron goes into this one and the cations around, it screens it. It sort of protects it, and then they stay there until you take it out, right? So how do you know that it is doing? Okay, you heard electrochemistry before. We also do some electrochemistry. So what we do is, when you scan this viologen, for example, it shows a reduction potential here. That's a reduction potential. And you become methyl viologen to viologen. So, but when you come back, what you see is this one should be here and this one should be here. Methyl viologen reduces around -0.2. And so when you come back, we should have gotten back a reversible peak, because the anodic and cathodic peak should combine. But when you read, again, my apologies, this should be down here and this should be down here, okay? This is ferrocene. So nothing happens, and the electrons are there somewhere. We don't see that back electron reduction. But if you have a ferrocene in the solution, the ferrocene gets oxidized, right? And then when it oxidizes, it grabs that electron. As a result, although it should be very small, you get a very high current. And you can test this one by reducing at different wavelength, and this peak height depends upon how much viologen is. So what you have done is, you have reduced methyl viologen to this viologen radical that gives you an electron, and that can just propagate and react with this ferrocene molecule that is being oxidized. So it is just a demonstration of an electrocatalytic process. That means you can enhance the detection of this ferrocene by just having this kind of a species. So it is very commonly used, but that's what it shows the ferrocene in this one. Okay, we can also do another experiment. Again, you can go and try it. It's very easy. So basically, we have a semiconductor on a graphene sheet, and you want to transfer electrons first to this sheet, and then you go and in another catalytic surface, you can do it, reduction. So now you are separating your oxidation and reduction on the same graphene sheet, and this one is just an electronic conductor. Okay? So how do you see this kind of a process, right? So what we did was, it's very easy. We first took this titanium dioxide. I don't know whether how many of you work with titanium dioxide, but if you make an ethanol solution and degas it and hold before a UV lamp, it turns blue color. Okay? And the blue color is coming from these electrons that is trapped in the TiO2. We call it trapped electron. Essentially, it is Ti3 plus centers. Okay? That's the blue color you get. So when you shine the light, you get this blue color. Okay? I don't know how colors see. And to that one, now you add this graphene oxide. So when you add this graphene oxide, the color sort of decreases. It should become lighter color. And you should have only the reduced graphene oxide color. I don't know how well you see from the back. I don't see much difference here. But it does become, this blue color disappears and becomes more blackish color because of graphene oxide. So that means these electrons are consumed, right? So the Ti3 plus which is there, now this electron has moved into here. How do you know that the electrons are still there? Okay? So what we did was we added silver ions. When you add silver ions, if there are electrons, we should reduce it. Since there is no blue color in the TiO2, we get electron must be from RGO, and sure enough, you can see a color change right away. So basically, you excited this one, transferred electrons to graphene sheet, and then it went to the Ag plus and do it. And actually, you can titrate it. If you have absorption spectroscopy, you can titrate it. We looked under the microscope, and you can see here, sure enough, all the silver particles are down here, and the TiO2 particles basically go on the edges. And again, that's the silver, and that's your titanium. So you can identify elemental barrier on the graphene sheet it is. So you can use this for various purposes, how you can do this reaction. So now the question comes, if you make a film, can you do the same thing, right? So what we did was, we have a titanium dioxide film. If you have any titanium dioxide paste, you can put it on the top of it, okay? And then what you do is, that's how it looks like. It's a very mesoscopic film, small particles. Now you put electrophoresis. We make a graphene suspension, put this electrode in, and apply sort of a 50 volts or 100 volts DC electric field. In the electric field, this graphene sheet move and get deposited on this one. And you can control it, how many layers. If you look carefully, you can see some layers down here, right? So now you don't see this one anymore. So we know that on the top, the graphene sheets are there. It may be 1, 2, 3, 4 sheets, whatever. So now what you do is you shine from the back side of this electrode. So the first thing that is going to excite is your TiO2. And if it is a silver ions in the solution, the electron that is transferred to RGO, it gets in here and you should get silver. And what you get is this beautiful deposition of silver particles. Now you can also see this each layers that graphene sheets. It's a very easy method to deposit metals on graphene sheet if you have a TiO2. Okay? So, and then here is again deposition of silver is, this is, now you put a graphene sheet and then you shine the light, this one, and form the silver particles. And that's how it looks on a larger scale. And another beauty is you can control your silver ion concentration or the time of irradiation. And you can control the size of the particle. What happens is these are the seeds to begin with, right? That's the absorption spectrum of these ones. Okay, changing silver concentration and particle. See here, this is about 12 nanometers. And you can grow to be 16 nanometers. And this same particle starts growing if you keep on shining light more and more and more. And you can get 28 nanometers. You can just keep on continuing, and we take different samples. And this is 40 nanometers. So that is the beauty of making this method. It's a very simple method. So if you want to deposit metals on these graphene sheets, you can try this. Okay, you can try with other metals too. And people have used these kind of things. Again, this is not our work. People have used to make hydrogen. Once you have a metal and you have a semiconductor on the other side, you can excite it. Think about the previous one. Where is it? Yeah, so if you shine the light, you have a semiconductor here. Now, if this electrode is not there, and somehow you can peel off this one, you can shine the light, you can get oxidation process here, and you can do the reduction process on this one. And that's what people have done studies in this one. People have also used what they call Z-scheme to separate these two particles like bismuth vanadate and a ruthenium strontium titanate catalyst to do the reduction and oxidation. And this becomes sort of a bringing them together, and that's what they have reported. We have also, again, it's not only in photocatalysis. People have used it in fuel cells. That's what we use. We use graphene oxide, platinum, just to have favor this one. Again, these are the fuel cell characteristics. The pure platinum showed not much performance, but the graphene oxide platinum showed much better performance. Okay. So again, it's a fuel cell. In the fuel cell, you bring hydrogen and oxygen and make water, and you get electricity. So typically in water electrolysis, when you pass electricity, the thermodynamic potential is 1.23, you get hydrogen and oxygen. If you reverse the process, you bring hydrogen and oxygen on a catalyst surface and make water, you should get theoretically 1.23 volts. You will never get to 1.23. Probably you get about 0.8 to 1 volt. Okay? But you can see here, as you start drawing current, it drops down, and that's the fuel cell part of it. Again, people have used for lithium ion batteries. In the case of lithium ion battery, you have, again, this is graphene oxide, and these particles, they have used various, this is somebody else's work, just to show you how these are the ones, they charge-discharge curves. They plot it to show that having graphene makes the performance of the batteries better. Again, there are lots and lots of studies, people using graphene oxide. I just picked up one showing you how it is. Alternatively stacked single layer molybdenum sulfide and n-doped. Molybdenum sulfide is also a 2D material. So these guys have made a stack, alternating stack of molybdenum sulfide and carbon graphene. So you can see, imagine having these 2D sheets, how many different combinations you can get in and explore these things. Again, they have done it, they have shown it here, and they use it for batteries, and they said that it's better performing batteries. This potassium intercalation on ultra-thin graphene electrodes. So there are lots and lots of papers on batteries. If you are looking, find out how people have accommodated these graphene sheets to create these lithium-based solid electrolyte interfaces and then made these materials. Unlike the substantial plating occurring in K plus containing electrolytes, so that's the problem with the potassium ion batteries. So this they get discrete staging type phase transitions they can see. So again, this is another application in batteries. We have used it in solar cells. Again, mixing, this was in quantum dot solar cells. When you mix these graphene sheets with this one, the electron flow is better and they shuttle the electrons. Like they can collect the electrons when you make the stack of these particles and do it. They have also been used in organic PVs. This is just like you heard the talk yesterday. You can use these organic PVs with the graphene and they claim that it was better. People have used in the perovskite solar cells. So it is a very common process. So again, there was between say 2010 and 2020, people were putting graphene in everything and were claiming that performance becomes better, right? So that's, again, this is another one to show you when you have graphene in a TiO2 film, you can increase the photocurrent. So this another one is the transparent photocurrent. You can use it top contact because a single layer graphene absorbs about 2% light, but it's also conducting. So one of the things in solar cells is you want the top layer to be transparent, right? That's why people use FTO or ITO because it's transparent and conducting. So people are trying to find alternate ways to make contacts. And graphene is one of them considered. So people have used these graphene contacts and make, in fact, in most of the solar cells, if they make commercially, the most expensive part in the solar cell is the indium tin oxide glass. The rest all things are cheap. So that's why they want to find alternatives. So you can use, and this is just a demonstration, but also for silicon solar cell as top contact. In the top contact, if you see the silicon solar cell, they have a silver contacts. You see these white lines, those are silver. 8% of the silver produced currently goes into silicon photovoltaics. They are worried that if the silicon demand goes up photovoltaic, where you will bring the silver from. So that's why they are also looking for alternate contacts. So this is where you are. So as I said, there were so many people were doing, and these guys did an experiment. Say, let's see what happens. Will any crap we put into graphene increase an electrocatalytic effect? So they literally put the chicken poop into these cells and showed that indeed it informs. So this got a lot of attention and sort of bring down sort of the whole hype of graphene. And now people are very careful. Don't get me wrong, it is still useful material. It is being used in a lot of applications, supercapacitors, batteries, and everywhere. But when you make a claim, just because you are adding graphene, you are making better, should be more examined. You should give a reason why it is happening, right? You should explore it. Just because you added making better doesn't make any difference. So that's one, that one. Again, this is giving you some lighter side too of this one. Graphene for solar cells. So another application is because it is black, and you know anything black outside, it becomes very hot in the sun. So there is a lot of another research that's going on is desalination of water, because we need good drinking water. We have sun, we have seawater. Why not we design something that seawater will go up and evaporate and collect? So for that, they have used this graphene material, and in fact, they can make it float on the top so that the sunlight comes in, heats up, and they can even heat it up, use the hot water, or you can use the vapors and condense it. So that's what they are trying to do. Again, this one came out in Nature Energy a while back. Solar thermal energy harvesting, another one. So same thing here, right? The evaporation process can combine vapor generation. So I'm just giving an idea how various places this graphene has been used. Again, this is a hot area, so how they do it in this one. Okay, so that's about the story on the graphene. Okay, there may be more applications of graphene, but our more interest is in the energy conversion and storage, and I gave you several examples. Now, again, the discovery of graphene led to explore other 2D materials. Okay, so we'll talk about it. So one of them, the most recently you see in papers, they call 2D perovskites. These are essentially metal halide perovskites, which I'm supposed to talk, the first talk, which I'll be talking tomorrow on the 3D talk. But they are like the structure like this. They have got this lead halide, lead iodide, lead bromide type thing, this network. And there is a cavity here. And then there is the A side cation, which is cesium, methylammonium, or formamidine. So they go inside and sort of bend to give you that perovskite structure. Now think about the cation is a larger size cation, right? What will happen? So what happens is if you put a larger size cation, so it sort of splits up. And now you get these 2D layers. So that is the low dimensional perovskite you get it. And again, there are 3 different types. One is called Dion-Jacobson. In the Dion-Jacobson, if you see the functional group, there are got 2 ammonium groups here. And what they happens is this one and these ones are aligned, right? So because they go and bind same molecule. But if you have only one, like butyl ammonium, so it binds to the one of the sides, and then this one binds it here, so you got little bit staggered structure. So if you see here, this is aligning with this. Here, this aligns with this. So again, they are called Reddelson-Popper type. So again, it is controlled by the what type of the spacer cation you use. If it is a diammonium showing same thing, it just gets squeezed between the two. If it is single one, one attaches here, one attaches here, so you get this one. And this is all inorganic type thing. Again, CS2, PBI to Cl2 type, what they call this 2D structures. Okay, the Reddelson-Popper. So if you use it, you can butyl ammonium or phenylethylammonium, so PEA. So these are one of the commonly used compounds. So when you are making these ones, to make them is very easy, okay? So you take methylammonium, lead iodide and lead iodide, mix together, heat it up, you get it, these things. But instead of methylammonium, you add ratio of methylammonium to butyl ammonium, you get these structures, okay? And when you get it, even you can crystallize them. That is the beauty of it. And then you can redissolve and make films for whatever studies you want. So that is the peak you get. There is a strong excitonic peak. Yesterday, Professor Patil mentioned you about this excitonic energy. If the binding energy is strong, you get this peak, very sharp peak. So that's what we are getting in this 2D perovskite. And as I mentioned earlier, the ratio of this cation, methylammonium to, in this case, PEA, phenylethylammonium cation, right? So when it is 100% methylammonium, you get this bulk type behavior, okay? These are all 100%. If you have 100% PEA, then you get N equal to 1 because there is no methylammonium there. So you have got one layer sheet. So we call it with the number, these are layer numbers. But if you have a between methylammonium and layers, so you can get N equal to 2. Between 3 and 6, it becomes a little harder. You get always a mixed thing. So you get these different peaks compared to 2 and 3 type things. And you can number of layers versus band gap energy. So that is the peak. It starts shifting, shifting, and shifting. This becomes bulk. So this is a higher energy transition. You can see here this one is around 420, whereas here it should be around 550 or so. So if you plot the band gap, you can see here the one n equal to 1 has larger one. You can see it's almost colorless. And as you increase the layers, it becomes larger. So you can also do the transient spectroscopy, see how the excited state. Now you can see these different bleaches. You can get the lifetime of this excited state or these charge carriers. If it is n equal to 1, they come down very fast because the binding energy is so fast, they just recombine. If it is 1, 2, 3, as you increase, that becomes easy because these just come. So you can, the charge carrier lifetime, you can see here, decreases with the decreasing number of this one. So this is also been projected as a quantum well structure. So you have two types of materials here. One is an organic and one is inorganic. The organic typically has a large band gap, and this one has a smaller band gap. So as a result, these charge carriers are bound very strongly, and that's what you get this one. Okay, that is just brief about 2D, but this field has really exploded. If you want to adventure it, see what it is. So for example, these guys have done machine learning assisted screening of these ones. So they have, you can see here, variety of these molecules. And they say that and they use it for solar cells and to improve it. And what they found is some of these organic ones are better in terms of the improvements that you see in the solar cell when you add it. So people just add on a 3D layer, one small layer of 2D to do it. You can also design with this spacer cation like naphthalene. Naphthalene is a photochromic molecule. It generates triplets. So what we saw was we can exciton this lead bromide, can transfer this energy to this naphthalene, and we can follow this triplet. And so that's the absorption of your NEA2PbBr4, and that's the emission for A, and you see this naphthalene excimer emission. So this is the one that got transferred. So you can play around with different things. So especially it makes it very interesting is you can put a lot of chromophores. People have used in solar cells, and as well as they're made just with these kind of materials. They are not as high as the 3D type, but they do show it. People have made LEDs with these materials. So there is a lot of interesting things that goes on. Okay, that's about 2D perovskites. Again, the field has grown in the last 2 or 3 years a lot. So I suggest you to take a look at some of the papers that are published in recent. Lastly, we have Max things. This one is based on this transition metals. This one. So these are the ones they use it. And essentially, for example, they take titanium and aluminum and one of these metals, and then they take away the aluminum to give you these 2D sheets. Okay, so they call it MXT. So, and what are the different types? You can find it here, which is, so here they use it for photovoltaics, these machines. Here is another one, transition metal dichalcogenides. Again, here, these are called TMDs or TMDCs. They are using for electrocatalytic purposes, photoelectrochemical or PEC type reactions, or photocatalytic reductions. Again, these TMDs is basically metal dichalcogenides. It could be like MOS2, right? So those kind of materials, people have done it. Again, a lot of works. We have been working with the molybdenum sulfide. If you want to do, there are various ways of taking these sheets out, right? In the beginning, I showed you this, the bulk material looks like a book. So you want to take it as a individual pieces, right? Most of the time, what you do is your book gets wet in the water. What happens? All these leaves become separated. So people use various techniques to separate out the sheets. And one of the things, easy one, one of our students found out was, this is again from the literature, you take this molybdenum sulfide wire that you can buy it from any outsource source, and then you stick it in and then put another counter electrode and apply about 20 volts or so. Do the electrolysis, okay, in presence of a large cation. So what happens is this electrode becomes charged, negative, these cations intercalate. Just like your lithium-ion batteries, how the lithium-ion goes into this intercalation. So these one, they go in, and this wire becomes like size of 1,000, like a sponge. And now you take out that sponge and sonicate it, and you get this solution, right? And then you can, depending upon the speed, you can take either 1 or 2 layers or multiple layers, because depending upon the speed, you can take away the supernatant. And here is the one, it's maybe 1 or 2 layers. You can see here molybdenum sulfide, and you put some silver ions and shine light, you can form silver particles on top of it. So we were studying the photocatalytic processes and also the excited state processes, the charging effects, all these things, they're doing it. Here is an example to show you a reduction of viologen using these things containing silver. And having silver, it really enhanced the reduction efficiencies. So we are trying to use it now for hydrogen production, these kind of materials. Okay, to summarize, graphene oxide can be readily modified with metal and semiconductor nanoparticles for catalytic applications. And I gave you a lot of different applications. Batteries, I didn't talk about supercapacitors, but they're also widely used. But for energy things, you can modify these ones. And the beauty of this graphene oxide is already has a functional groups. If you're talking to any organic chemist, once you have functional groups, you can attach. Any planar molecules like porphyrins, they go very like to sit on the graphene oxide. So you can make different solar cells and those kind of things. A good viscosity for intercalation of ions and facilitate collection of charges. Emerging 2D materials offer new ways to expand. Okay. Again, what is the outlook? There is a large-scale manufacturing with a lot of consistent quality and functionalization. You know, any product you want to have a same property. So with graphene oxide, it's very difficult. The batch you make today and batch you make next week may differ, or the person to person, because it's a chemical oxidation for a long time process. Again, another one is to have it electronic properties, you need to have good conductivity. So that is a challenge. Long-term stability of exfoliated graphene sheet, for example, in storage batteries. They don't want you to collapse and lose that capacity into other 2D materials, and keeping up production with the demand. Okay, so there is a lot of people involved in our group work with the graphene. They all graduated and have some job somewhere, so just to thank them. Thank you very much.
Just to open part discussion.
Molybdenum sulfide and selenide. Selenide is also two-dimensional?
Yeah.
Selenide.
Yeah. That one also, tungsten also. People have done with tungsten
sulfide.
Working with tungsten sulfide. They can be same thing.
But
what is surprising is the molybdenum sulfide it has been now used for hydrogen production directly. And
But the rate is very low.
Yeah, but it is stable. So
Millimole.
it is, yeah,
Micromole.
everything is in micromoles. People, whatever you use, report is micromoles to maybe a tenth of a millimole.
But as compared to other applications, MOS, as compared to graphene, MOS2 has less applications.
Yeah.
So even though it has a two-dimensional, so what are the probable reasons?
MOS2 has what?
Has lesser application as compared to graphene.
Lesser
If you
application.
see graphene, so n number of
Again,
applications.
it's a popularity, right? So how one uses and the other uses. Actually, right now, more people are using these TMDs than graphene. Right now, if you look into the papers, there are more papers on this one than graphene.
So as compared
Because here also, molybdenum sulfide is also a semiconductor. So you can explore the semiconducting properties also. Yeah.
Sir, for the synthesis of metal dichalconized,
Yeah.
so what are the strategies for the selections of different metals?
Transition metal dichalconized,
transition metals,
TMDs, right?
yes.
Yeah, what do you want to know?
We have to make the metal dichalcogenides.
Yeah, this one to make it the. Oh. I have to go through all these ones. Yeah. So this one you can exfoliate, just taking a bulk MOS2, or you can do the, you can also do CVD also. So what is your question? How do you make it, or?
Synthesis of metal dichalcogenides. Emixin. Last slide, sir.
This one, right, or this one?
No, last.
So question is that, sir, so what is the criteria for selecting the metal of the metal?
Oh, okay. Selecting for Maxins, or you want to do? Yeah. So again, most of the work is done with titanium, and you have carbon, and it could be sulfide or those things. So you have carbon is common here, and A could be anything. People have used various ones. You can check one of these articles, they will tell you. But this is a rigorous process. What they do is they have aluminum to begin with. So you have to make that material, right? So whatever you have, you pick one of these M, say titanium. So here you put aluminum or whatever zinc, and then you can put carbon, and they just heat it up. And then what they do is they put hydrofluoric acid that dissolves the aluminum in this one. So they are layered structure. So these layers sort of separate out. And they say that they can make it even kilogram quantities in a day. So again, this one is very popular in China in the research. In the US, there is Yuri Gogossi. He is pushing it very hard, doing it, but not many other people are using it. The question here is making this one is it's not difficult once you are making it, but it involves hydrofluoric acid. So one has to be very careful.
Sir, one question.
Yeah.
Recently, borofin is one of the rising star material in material science. Borofin material.
What's the material?
Borofin.
Porphyrin.
Borofin.
Borofin. Okay, borofin. Okay, with boron.
Yes.
Boron. I didn't talk about it. So
It's one of the rising star material in material chemistry. So, what is your opinion about the borofin instead of the graphene or graphite?
I think making it will be harder, right? Graphene is making is very easy, like graphene oxide, for example. Porphyrin, you have to really make with your CVD type setup. It's not naturally occurring. So that is the thing, how fast you can make it in a large scale. That becomes a problem.
So, the TiO2 RGO and CO are totally composite. And with photo irradiation, the size of the AG is increased.
Yeah.
What is the mechanism?
It's very easy. Mechanism is easy. So when you go in here, initially what happens is, yeah, this one, yeah. So what happens is initially when you have these ones, right? So you put graphene here, so it sort of disconnects with TiO2, right? So there is no TiO2 exposed anywhere here. So that's the purpose of showing. So here you have TiO2, and now you are putting a thin layer of graphene oxide. So now when you are depositing, these ones have defects. So most of the time the metal ions, they go on these epoxides. There are papers showing that it binds to the epoxide. So initially what you have is, when you start it, so you form these seeds. They act seeds, right? So one of the thermodynamic mechanism is a metal ion can be reduced on a metal surface with less energy than any other place. So when you shine the light like this, you already form the seeds, right? So now the excess silver ions either go on a blank space or it can go on here. But this one is a lot easier to reduce. So that's why you see the particles grow. So if you see the density, again, it's not in the same spot, but you can see they are not just packing like crazy, but they are just increasing in size, right? So just increasing in size, doing it, but consider like compared to here and here, they just increase the size. So the same particle starts growing. It's like a seeds growing bigger. And again, a lot of people in the synthesis also, metal particles, if you want to grow bigger, you make first the seeds and then ions, and those particles grow. But again, you can desire size. For example, if you want to study size effect on this photocatalysis, you can just make it different sizes and then use.
Thank you, sir, for this enlightening lecture on 2D material, graphene and beyond. Ladies and gentlemen, we'll now take a short break to rejuvenate with some tea, and let's take a moment to unwind. Please ensure to return promptly within 10 minutes so we can continue with our engaging lectures. Thank you. Enjoy your tea. I kindly request all the participants to circulate the attendance sheets properly.
I changed some chart, either the old talk. Okay, we are continuing the themes, again, materials for energy. And one of the popular topic is photocatalysis, right? A lot of people have worked, and this field has grown quite a bit, right? Anybody makes new materials and wants to use photocatalysts. And there is different similarities between electrocatalysis and photocatalysis, right? In electrocatalysis, you can convert to electricity and use that electricity and use an electrocatalyst to develop these value-added chemicals. In photocatalysis, you are directly exciting a semiconductor photocatalyst. So you don't need this one, right? That's the whole idea, is to exclude that the middleman, which is solar panel or something to generate electricity, so we can do it and do the same thing. So both these areas are very active. One of the things you can also do is you can convert these photons into electricity and use that electricity to drive LEDs. Okay, this is one of the secret, right? Everyone thinks when you make a photocatalyst, you need to put it in the sun. But everybody does it in the lab. But think about even in industrial scale. It's very difficult to go and put in the sunlight. But if you have LED as a light source, it's very efficient. For example, if you want to excite at 350 nanometers, your TiO2 or whatever oxide you have, the sunlight has very little efficiency, less than 2%, 3% light of the entire sunlight. So everything else is just heated your system, right? But now think about using silicon. Silicon absorbs all the way to 1100 nanometers. It is capturing all the photons until 1100. So you have at least 50% of photons it absorbs and converts into electrons, right? And now you have LEDs that are 75% efficient. So if you take it, you can even get up to like 40% of the original photons back in here and use that one. So compared to 5%, you have a large number of photons now. And they are cheap now, LEDs. So think about doing your experiments with LEDs also, and you can tie it up how you are going to use electricity to renewable to do it and do the same thing. One of the things in electrochemistry, when you are studying, they are monitored. These are the main monitoring thing, right? You monitor current versus voltage, or current versus time, voltage versus time. The rest all are derivatives. You can get J and V and get your power characteristics. So this is what you measure. If you go into these ones, you monitor absorbances versus time, or emission versus time, for understanding what is happening when you induce this process. Of course, you are measuring the products and other things, trying to tie up with efficiency and those things. Okay, again, electrocatalysis versus photoelectrocatalysis. Again, electrocatalysis, as it suggests, you have a membrane separating an anode and a cathode, right? So, and you pass the electricity with a control potential with a reference electrode, and you can do the reduction or oxidation. So that is very simple, everybody's followed. In here, now you are replacing, say, for example, anode with a photoanode. So now you don't need any external power supply, so that when you shine the light, you're driving these electrons to the counter electrode, and the holes come up and they do the oxidation. So that is the basis of photosynthetic PEC cell. In the regenerative PEC cell, what they do is they use a redox couple. So whatever is oxidized here gets reduced back. Right? For example, if you have iodide, triiodide couple. So that's what it happens. So it just shuttles around and keeps it regenerative. Again, they need an external energy. In this case, it's electricity. In this case, it is light. And many a time people combine both. So they will apply a bias here that you are applying an external energy, okay, in addition to light, to boost your things. You can also do another way. You can use, this is what we did in 2015. You can have a solar cell in tandem with a photoelectrolysis cell. So here you have got a perovskite solar cell that is attached to this bismuth vanadate, right? So basically when you shine the light, bismuth vanadate absorbs the light. Whatever the light that transmitted through excites your solar cell. That gives the enough bias to drive this oxidation reaction, and you can collect hydrogen. So although there is a bias here, but it is driven by the light. You are not using an external source. So these kind of tandem structures are also very interesting. So how you are again coupling with the battery and this one. So again, the energetic here is the bismuth vanadate, you oxidize, and here you got platinum, you oxidize. In between, you are shorting this one. Okay, so that is, you can go and take a look at the paper for more details if you like that approach. Photocatalysis with semiconductor nanoparticles. Again, I showed you this slide yesterday, and one of the things in photocatalysis, please remember, this is true for every system. The recombination of charge carriers is the most favored pathway. That's why efficiencies are low. The one way to boost this one, they're inherently inefficient because of the thing. Before the electron goes out, this one will recombine. The only way people do is they put these co-catalysts, call it. And for example, if you put metal, they can drive. And so it's basically you have to compete with this recombination process so you get little higher yield. And the other one, which is most common, is people will use sacrificial donors. Okay? So, and typically this is in molar concentrations people use, very high concentration. As you know, increased concentration is a probability of taking away the holes is much better. So now these electrons are excess, then they can do the reduction. And then people can claim high efficiency. But this is the one they need it. If you are using cadmium sulfide, there is no way you can get hydrogen and oxygen. You have to use this one or take those holes by some other means, by applying a potential or whatever it is. Okay, the early work, right? This is not a new field. This is a century-old field. These were some of the early good works that came in, okay? So go and read these papers. They are very good papers, thorough, mechanistic, they analyze the products, tells you how good a study should be done in photocatalysis. Not just observing dye degradation. You need to go beyond that, right? So this is, again, they were organic compounds. This is the first C here. Even at that time, they call it highly efficient deethylation of rhodamine B. This is another one with methylene blue. 1978-77. Okay. This is another one. Semiconductors, Bard had a review article at that time. Very good articles. Then in 80s, they followed more papers. People were interested in degrading organic compounds. It was very effective in air purification, but people wanted to see whether we can take different one, like the chlorophenol was one of the standard everybody used at that time, because all the mechanisms and all those things, they do it. And these are some of the early people who studied photocatalysis. Many of you may not even remember the name. Please read their papers. A lot of interesting information. This is one of the Alan Barr, and he said photocurrent enhancement via trapping of photoelectrons. So it is very simple. He made a titanium dioxide slurry, put electrodes, one in the light, one in the dark. You can get a photopotential. So these particles, they were getting charged up. They were giving electrons to the electrode. It's the first time somebody showed that, okay, these particles can have charge. Again, you're talking about 1982. Here is another one, Arnam Hengline. He has passed away. He is one of the early ones in all nanoparticles. He has studied extensively metal particles. He has extensively studied semiconductor particles. He has also done sonochemistry. So very well regarded. Probably people know his student Banneman. Then Michael Gretzel, he was earlier, before working with dye-sensitized solar cell, he was working with colloidal semiconductor particles. Then okay, this is our work, studying these spectroscopy aspects, right? I worked with Marianne Fox. She also passed away a couple of years back at very young age. Nick Serponi, he's now in Italy, retired. So we all studied the excited state properties, right? So that was 1980s. Then comes 90s. So this was still hot topic, environmental remediation. Then also people were working with solar cells. And then the offshoot started with dye-sensitized solar cell. Okay, I'm just giving you some history, how this field developed, right? Okay, then domination of photodegradation of organic, it was a really hot topic. Fukushima, this is even, he gave me a train card with Toshiba and TiO2 on it. There was a lot of these studies. They established the degradation mechanism. For example, hole versus hydroxyl radical, right? Because when you generate these electron and holes, the holes come to the surface, and typically oxides have hydroxide ions around it. And these hydroxide ions can react with holes and form hydroxyl radicals. And that is one pathway to get hydroxyl radical. The molecules can also adsorb on the surface and can directly extract the holes. And the oxidation products are different. I'll show you an example. And direct versus sensitized. A lot of people use dyes, right? They see the dye degradation. What is the mechanism? Okay, there are different ways a dye can degrade, right? Have you understood how it is done? Or just saying hydroxyl radical reacts, right? So you can do a lot of tests for this. Combining with other advanced oxidation processes to boost this one. Again, this is a very success of TiO2 photocatalysis. There are a lot of products out in the market. Again, challenges remain. This hasn't worked yet. Everything works in your deionized water in the lab. You take the real wastewater, it will not work. Or even if you take tap water, it may not work. 2000 onwards, there is a flood of demonstration of degradation, various dyes and other organics. Till today, a lot of work, right? Despite very interesting advances, has not produced any practical devices for water treatment. You may claim in your paper, I want to study for water treatment, but nobody has produced yet. You also have these papers, right? The Otani, he published A to Z, what we know and what we do not know about scientific science. This is on photocatalysis. Again, these are good reviews. That's published a little older, but they gave you the latest on this one. Okay. Who coined the term photocatalysis? I gave you some 70s. Any idea? You have to go in 1955. Okay? This paper. Please read this paper. It's a beautiful paper. 1955. Write it down. It's worth reading. And its title is Photocatalytic Properties of Oxides. And they published in Journal of Chemical Education. She was a teacher, Sister Maria Claire Markham. She did an undergraduate lab experiment with zinc oxide suspension. She showed hydrogen peroxide. When you shine the light, it generated hydrogen peroxide. But if you put the hydrogen peroxide, it also degraded hydrogen peroxide. So there is always a steady state, same concentration. So she showed through that one how this forward and back reactions, like the same zinc oxide could oxidize or reduce the same thing. So again, with these oxides and studied their photo reactions for the past few years, one of the most unusual in these oxides is zinc oxide. Reactions seem to be of particular interest as a possible conversion of solar energy to chemical energy. At that time, she pointed out, right, that this can be used for solar energy. That's what most of you, if you're working, you have to owe her these ones. Again, there are also questions about radical intermediates. Who did it, right? That's again Bard. He published direct observation of radical intermediates in the radical formation by EPR. So they use ESR or EPR to characterize the radicals form, because that is the first time they found it. So then we got involved, and then we studied. I wanted to, if you have a particle, it's very difficult to do selectivity, right? But the same particle, if you put on an electrode surface, you can drive these electrons one side and holes one side and bring in the selectivity. Because at that time the questions were there, can it be making it selective? This is the most simplest approach, to put particles on an electrode surface and drive these ones opposite side. Again, so this is one of our early studies in '94. We studied the degradation of 4-chlorophenol. Because at that time, people were not sure, there were controversy, whether this reduced oxygen, when you got, whether that is also reacting. By separating it out, we could analyze the products that were here, 4-chlorophenol, that is gone in, and we can show that with applied bias and then do it. And more importantly, we could show, remember in the earlier I showed you, these holes that are generated, either directly they can oxidize the molecule or the hydroxyl radical. So there is different pathway. This is the hydroxyl radical pathway. The first thing is the hydroxyl radical attaches and gives you this series of products. We analyze the products. We had a computational model to explain why this pathway. If you have a direct oxidation, right, you form this product here, this radical, and then you get a totally different products. So based on this one, you can analyze how it is. We can direct oxidation or hydroxyl radical. So we can differentiate these ones. So again, that kind of a things we did very early on. Another thing we used was 2,4-D, 2,4-dichlorophenolic acid. It's a herbicide. It goes into a lot of water, okay? Because people use it for killing the weeds. In the farms and everything, if you don't want these weeds, it selectively destroys these large leaf weeds. For example, it doesn't affect the grass, right? I saw in the morning the people were picking up the weeds in front of this one, right? So that is probably, from an environmental point of view, the best way to do it. But the easy way to do it is spread this one. It takes away all this unwanted broadly, but it leaves the grass fine. So it's a huge product, and we can see its degradation over the time. But there is another intermediate comes in. This one grows in, and then it decreases. If you take the TOC, you see this TOC going very slowly, total organic carbon. That tells you how much organic is left. That is slower, right? Your parent compound is decaying much faster, And this one is slower because you have got intermediates that are formed. So this one clips here and forms this chlorophenol. Okay, so then the question came, can you speed up this process of this one, right? So we had another talented student, and earlier people were asking how to make these new techniques or devices. So if you have think differently, you can always come up. And I just suggested, we want to combine these two because we are also doing sonochemistry. And Naomi Stark, and now she is faculty. She was an undergrad, and then she came up with this idea to do this. One is you put the sonolysis cell and shine on from the top. Another one you do sequential. You do in one compartment photocatalysis, another one sonolysis. And again, there are several advantages of doing this. You mass transfer improvement, rate and efficiencies, and minimize the intermediates. Remember I showed you the intermediate? So when you do it together, what we found out was the degradation was much faster. When you combine the both, the rate was much higher. This is the rate of degradation of chlorophenol and 2,4-D, much higher, and then either one of them. So that is the advantage we had. That's the sonolysis cell when you can directly shine light on the top of it. So again, I'm just saying these are simple variations, not major breakthroughs, but how one can think designing something with your existing photocatalysis if you are working with it. Okay, think something additional one, then repeating the same thing for other things. So again, here it is the mineralization. If you take TOC, if you use sonolysis and combination here, much faster. Okay. But the most popular thing everyone tries, right? Dye degradation. Because it's very easy. It's not challenging. The one I showed you, chlorophenol and everything, you have to do a lot of product analysis. It takes a lot of time. We are in a rush. We want to publish that paper. This is easy. I put dye, put it in front, take a spectrum, it decreases. Oh, my catalyst is active. This is better than the other catalyst. And then you send it to paper, the journal rejects the paper, then you worry, why did they reject? The reason is it's been hundreds and thousands of studies. It doesn't tell me anything new, right? When you write a paper, it has to convey something new that is not known, okay? So again, this here is an article long time back, 2006. Probably no one reads it. Is methylene blue an appropriate substrate for a photocatalytic activity test? A study with visible light responsive titanium. So he discusses in that. The reason is dyes are rich in photochemistry. They also absorb light too, right? They can undergo degradation by a variety of photochemical methods. Does not directly provide mechanistic insights. Just you measuring decrease will not tell you anything. Can interfere with light absorption by the photocatalyst. Again, earlier studies mostly use phenols. They didn't absorb in the region where your catalyst was absorbed. There is also a standard developed. If you use phenol and you saw the degradation, like an actinometer, it's 10% efficient for TiO2. So then you can compare, you can calculate the efficiency. So that's where, because no one reads older papers. The reference I showed you, please read. A lot of good information, how to do the right things. Now I will give you 3 different mechanisms, okay, with dye can degrade. Again, these were done in 90s, okay. So we were very much, one is UV versus visible excitation. So when you have UV light, this tends to be the more preferred way, direct oxidation or this one, and you get the product. If the dye is absorbing, it can put an electron down here and become a product. Don't believe me, take TiO2, put a dye in some ethanol solution, evaporate off the solvent. You get a colored TiO2, right? Leave it in the light. Within 2 hours, its color will go. And the mechanism is not your catalyst doing it. It is this mechanism. It is putting electron. Electron is taken away by oxygen and the dye gets bleached. So it is simple experiment. You have to ask questions. What other mechanisms can do? Remember yesterday I talked about burden of disproof. So again, this one. So reductive pathway. Dyes can undergo reduction too. The O2 minus can interact, right? So again, that one, conduction band electrons, and again, and how to do it? Here is a paper. And we showed it how reductively this dye can be decolorized. This is by reduction, not oxidation. Because especially if you have it, this you already have reduction group, so it's much easier to reduce in this case. Oxidative pathway, direct oxidation versus hydroxyl radical. That's what I was talking about. These holes can be scavenged by D, or it can attacked by the OH radical. Here is dye degradation. Again, another dye degradation. So we use two semiconductors to show that it's better at that time. This is 1995. Again, degrades, right? Oxidative pathway, photosensitization. Again, you say that this, put it on a paper and you just shine visible light. You can cut off all the UV light and you will see the degradation. Okay. So again, the bottom line here is to tell you is you can okay to use dye, but provide a conclusive mechanism how and it degrades. Not just saying it degrades and you refer to some paper, oh, those people have explained it. Because your conditions are different, it can undergo by different ways. Okay, understanding the factors that dictate. This was the yesterday I mentioned this talk, and I gave you idea. In photocatalysis, one need not only what is forming or the ultimate thing that you get, but there are all these processes. Understanding that one, initially the transfer is very fast, but they can recombine back. Some needs to escape out of the surface to get stabilized, and they can also come back. So as a result, you get much less quantum efficiency for the product than what you start with. Okay, just this is bringing back that thing. Okay, so what we have been doing lately is, again, we are always looking for new ways to do it. There is always some student one interested in this. I said, we'll do something different. We will make a membrane, photocatalytic membrane. One way to make it is you can spin coat your catalyst on any surface and you can make a membrane, right? But there is another very easy way to make this one. And this was developed again by Bard and other things in the 80s. And it has not many people have followed it. And we decided to take another look at it. So things like Nafion. How many people know Nafion? Can you buy Nafion here? You can buy it, right? Yeah. So Nafion is basically a Teflon-based polymer. Very stable. It is used in fuel cells, all these membrane electrolysis, everything. So if you get it, buy it. It's not very expensive. It is just like a plastic, right? But what it has is negative charge because it has a sulfonate group, SO3 minus, inside the membrane. And they have pockets of 10 to 100 nanometers. 100 nanometer pockets connected by 10 nanometer channels. What you do is, if you dip it in any cationic, you put in your methylene blue, and all the dye from the solution goes into the film. It's a good cation exchange. Same token, you can put metal ions, right? If you have put cadmium ions, it becomes all the cadmium ion goes. Now you expose it to sulfide source, it forms cadmium sulfide. In this case, we are still working on it. We put first in indium, right? All the indium ions went in. You form indium sulfide. You put in zinc. You can form zinc sulfide. If you have both these ions in solution, right, you can get mixture of the two. And if you put it in an acid solution, they all dissolve and they come out because the proton goes in and binds to their sites. and kicks out all the metal ions because it's in higher concentration. Now you can take the solution and do the ICP and get the metal ion concentration, and you can see how much these two guys are. So you can do that. So this is one way to make a photocatalytically active membrane. I'll just give another example. Here it is. So we are exciting this indium sulfide, zinc sulfide, indium sulfide together when you shine the light. And our probe is our favorite methyl viologen because it has a nice absorption in the visible. We can see how quickly it is formed and doing it. And that's the kind of a cell we use. We put this quartz cuvette, they are connected by a O-ring here, we mash it and put between that photocatalytic membrane. It's very thin, right? But absorbs very strongly. I'll show you the color. And when you shine the light, you generate electrons. Electrons are driven on one side, holes are driven on one side. You can generate this one, right? So methyl viologen and this one. And again, we saw that there is a certain composition of zinc sulfide, the activity is the highest because that's where the charge separation. Both indium sulfide and zinc sulfide has a very low activity. So again, this is simple way of doing things. And if there is a gas, if you want to hydrogen, you can put platinum on this side, fill. And you can collect hydrogen and measure these ones. I'll show you another example how we did. Okay, so here is another membrane. So there is also called bipolar membrane. So what they have done is, that's a Nafion, which is cation exchange membrane. And again, these are commercially available. You don't have to struggle anything. You don't have to make anything. You just get it, get a piece, dip it in your solution, take it out and expose it. Just try Nafion. It works so great, cadmium, because you see the color right away becoming yellow. So what we do is, first, this bipolar membrane also has an anion exchange site. And this is sort of a little less stable than this one, but for your work, it works fine. And this one is already used in water electrolyzers, bipolar membrane. If you put in water, all the protons go here and all the hydroxyl ions go here. So the water dissociates within this bipolar membrane. And there is a membrane potential, right? One side is pH around 1 or 2, other side the pH, because of the hydroxyl ions, about 12. So you can see the gradient right there to drive these things. So what we do first is take this film, put it in the cadmium solution, soak it and leave it for 10 hours, let it charge fully, right? All the cations gets expelled here, and then we use this TAA, thioacetic acid, and warm it up about 90 degrees for an hour or so, 30 minutes. Then it becomes cadmium sulfide. You can also expose it to hydrogen sulfide or any other sulfide medium. That is fine. This one is, we use it specifically because it's a slow reaction. We want it to convert it very slowly. So it forms cadmium sulfide. Your film looks yellow, okay? Just like here. These are the actual pictures, may not be very visible. This is colorless, it becomes yellow. Now you put it in this one, it uses auric acid. Auric acid, AuCl4 minus, right? So the AuCl4 minus goes on this side. It loads up. Now what you do is you put it in your H cell and shine light. Your cadmium sulfide, you put some ethanol in this one to scavenge away holes, and that electron is sufficient to reduce this cold. And you will see color like this. So one side it is yellow, other side it's dark. Now you have got a membrane that is one side semiconductor, one side this one. So what we can do? Now we can do is we can find out how effective it is for hydrogen, right? So lots and lots of people have claimed all kinds of efficiencies using cadmium sulfide and some metal, and they use sacrificial donor. So we wanted to separate out the two processes, oxidation versus this one. So we put this membrane, one side cadmium sulfide, another side palladium, right in between, and shine light. And it was all first degassed, and we collected hydrogen from both sides just to compare how much hydrogen you are getting from real reduction and how much from this oxidation. Because all these sacrificial donors, they have a H in it. Even when you dissolve sodium sulfide, it instantly forms SH minus. The pH goes to 12 because you have taken away proton from the water. So that is this one. It gets oxidized. Methanol gets oxidized to give you CO2. Again, triethanolamine, this is ascorbic acid. All these things, they give you this product. So these are the collected hydrogen from both sides. And you can see here, that is from your actual reduction, from the side where you have metal catalyst. Side where you have your sacrificial donor also produces hydrogen. This is with methanol. This is with sodium sulfide. This is with ascorbic acid. And only the sacrificial donor that doesn't give hydrogen is sodium sulfide. And people don't like it because when they use it, they get less yield of hydrogen. If you use these ones, you get a higher yield, right? They don't separate it out. They just throw this catalyst with this one, with a sacrificial donor, and shine light and collect hydrogen. But actually, this is how asking questions leads you some new information. And this is what it is. Again, we are separating the two compartments using this membrane and collecting hydrogen. And you can see here nearly 30 to 34% of hydrogen comes from oxidation of your sacrificial donor, not from reduction. So that's why a lot of time, and I will show you later in the afternoon, there are papers claiming it to be more than 100% even. Right? So that's one of the problems, these ones. Okay, the next one is the new materials that we see is perovskite. They're coming up. Again, people are using it. This is another one. When you are using carbon dioxide reduction, any paper that you see CO2 reduction, check whether they have any organics. Okay? And most likely they will. They will use sacrificial donors like triethanolamine, solvents. Because photocatalysis, you know, has two parts. One is reduction, one is oxidation. Both need to be balanced. You cannot just have reduction. And typically what they write is reduction, the reaction write like CO2 reduction, and then they will say sacrificial donor plus whole products. What are those products? Next time when you see somebody writes the products, ask the question, what are these products? Are the products same thing what you are measuring in the CO2 reduction? Again, these have been, lot of photocatalytic applications have been used. This is the first one was hydroiodic acid making hydrogen from HI. This paper is wrong because of the graphene oxide, but get a lot of citation because this is one of the early ones they showed, but they have graphene oxide. I can guarantee you graphene oxide gets oxidized. This one, they converted some of these organic molecules, and here there was a polymerization reaction. Again, all photocatalysis. Photocatalysis in the sense that you are shining light on the catalyst and doing this reaction. Again, we try to look into it. You know, like, we don't just say all positive things, great things, because these perovskite materials, they degrade, right? They are not, cannot withstand polar solvent. So we wanted to see, and we did a lot of studies. The first one is, again, this is come out of a negative result. We made these nanoplatelets, again, following somebody's recipe. The problem was that if you add any solvent, right? So like say, this may be one of the acetonitride in this one. You add these things, you can see here the peaks start disappearing. In toluene, hexane, no problem, they're stable. The moment you introduce even a tiny percentage, it starts degrading. And what it forms is, it first forms this big blob and then find these cubes. Because thermodynamically, they are not stable. They are forced to stable with ligand. When the polar environment comes, that changes. So we couldn't use it for anything to study. So my suggestion was, okay, let's find out what is causing it, right? So we use different polarity solvents, and we can see this, the polar solvent fraction required to see this change. We plotted versus the solvent polarity, and you can clearly see a trend. And that became a paper. So next time when you get a negative result, if you can ask question and you can understand why that thing didn't work, it may be a paper, right? So you study Hamming. You can, if the problem doesn't work for you, change the problem. So that's the way we did it. But the bottom line is these nanoplates are not stable. What about excess ligands? Because you need ligands to stabilize these particles. But if you have excess one, in this case DDA+, they form 2D, two-dimensional particles. So your perovskite is not stable. So they change it, this one. Again, other people have found it. So you can see the shift in the spectrum here to get this two-dimensional things. Halide ion exchange, I was mentioning. If you have bromide and iodide, cesium or anything, cesium lead bromide or cesium lead iodide, you just mix the two. You see, initially you see the bromide peak and iodide peak, they change and you get a mixed halide peak. Same thing with the emission. You can follow how fast they exchange ions. If it is in a solid film, you can put it together and clamp it, you see the same thing. So it is very sensitive to the ions in the solution as it undergoes exchange. So if you are using for photocatalyst, it has to be stable, right? So here is another one. We try to put metal particles. In a small amounts, you can put this, deposit it. But when you shine the light, all these metal particles get ejected out of this particle and they form these larger clusters. So you cannot even put metal particles on these things. It's not stable, right? So if you add excess silver ions, it kicks out the lead and forms this double halide perovskite. So it becomes black. And you shine the light or treat it with lead bromide, it comes back again. So the spectrum goes from this to this, back again. So these are some of the uncertainties that is there. And again, as I said, once you have this problem, we want to solve it. And one can do is put a shell around it. And people have used polymer shells. People have used this wrapped polymerization and also coated with silica to give a surface more stability for the inside particle. And what we came out with is, since we like semiconductors, we made a heterostructure. We used two-step method. First, we made this cesium lead bromide, and then we added this cerium dodecyl compound, and then again treated, and we could get a thin layer of CDS. Okay, and we can do the elemental analysis to show that we have CDS, and the absorption spectra, emission spectra, and here is the stability. If you don't have CDS, emission goes away when you add 15% ethanol. Here initially it decreases, but it is stable. So again, you can make film, you can deposit it, and everything you can do it. Again, we studied the electron transfer reactions, and we can now just these electron transfer processes. And this one was not, we could not do it. The back electron transfer was much faster. Here we can stabilize the product. You can see here, you can stabilize the product. You can form this methyl viologen radical that you see here. And you are seeing, we use that as a probe to study electron transfer. Okay. because it's a stable radical and it gives you a lot of information. And again, you can see here with time and absorbance, you can follow how is your yield, and our yield was 8.4% in this way. Another interesting thing, like you might have heard about in semiconductors, people talk about conduction band, valence band, Fermi level, the potential. And you can use this electrochemistry principle to calculate this flat band potential, which is essentially a conduction band, or Fermi level where it lies. So what you do is, this steady state irradiation, right? You continuously shine light in the presence of cesium lead bromide, and you form this cesium lead iodide. It reaches steady state and stays there. So at that point, you can calculate, the extinction coefficient, you can calculate how much reduction yield you have formed, right? And your initial concentration. And you subtract from the product, you get you the equilibrium concentration. Now you take that reduced product minus your original product that you after losing this one and put it in the Nernst equation. So what happens is your semiconductor band now equilibrates with this redox potential of this one, whatever the potential it is. And that potential is dependent on your E0 minus this factor. So based on that, you can calculate the E flat band potential. So for this semiconductor, the flat band potential for this one, minus 0.365. It will vary depending upon what surfaces you have, what pH you have, what conditions you have. But in a particle, otherwise, you cannot measure a conduction band. In the bulk, you can measure. So this is one way to measure your thing. So again, giving you an idea, we started with this photocatalytic reduction, but this kind of experiment can also give a feedback on this one. So doing more analysis of your data gets you newer information. Okay, so before we go for lunch, something to consider in the photocatalysis. Before making the next claim of highly efficient, it is important to consider the following points. Check the contribution of oxidative counterpart 2. Again, it applies for all other materials. Reduction reaction. Many sacrificial donors give you the same products. Check the direct participant support material in photocatalytic reaction. Sometimes you have support materials on which you deposit your photocatalysts. They can also influence your stuff. Okay, post-reaction characterization. This is one of the things hardly few people do, right? You always characterize before you do your photocatalysis. How many of you really do after you complete your study? Because that tells you what was the actual catalyst that was driving. Sometimes you have, for example, nickel phosphide, right? You may be making nickel phosphide, but when you run a reaction, it gives you a hydroxide layer. That is the layer it is catalyzing, not your nickel oxide. So it gives you what happened to your catalyst, that one. So if you want to do it, any photocatalyst study, characterize afterwards too, and show that whether it is the same or it got changed, that one. Again, all these limitations, if you are trying to do a reactor design, all these things for scale up is needed. And in the reaction medium while establishing. For example, if you dissolve carbon dioxide, most likely it is one of these three forms depending on the pH. Okay, if you have higher pH, it's carbonic acid. If you higher pH is carbonate, and lower pH is carbon. Okay, so this is what the LEDs I was talking about. So if you can, this is something to consider. If you want new approaches to do it, use LEDs. You can get a very selective monochromatic light. You don't need to use white light. Okay, it's as good as this one. Okay, so I think that concludes this talk, and we can all go for lunch. And happy to answer any questions.
Session is open for discussion.
Decolorization or degradation? I mean,
What is that?
photocatalytic degradation or decoloration of dye. Exactly what is the right term to use?
It's both are same, right? Because it degrades, it decolorizes. Because it is degrading, it is changing one form to some other form. Whatever that chromophoric group has disappeared. The dye has not gone completely. The molecules have not gone completely. It is just an oxidized form or a reduced form. Right? If you take a methylene blue or thiamethylene blue, for example, if you have in the lab, just put ferrous sulfate and degas it and hold before sunlight, it will become colorless. And the colorless because it's reduced. You leave it back to the air, it comes back again, color. It's a reversible cycle.
So what exactly is the right term?
So that is, again, it is a reduced form. So what I was trying to say is the changing of the color of the dye could be an oxidized form or a reduced form. In both forms, it can be colorless. So you don't know which mechanism was driving unless you probe in more to find out it is an oxidation process or a reduction process. So ultimately the dye change the form. If it doesn't come back, we call it as a degradation, right? So if it comes back, probably the decoloration is better word because it is a reversible process. Like I give you these thiazine dyes, thionine, methylene blue. The reduced form is called leucoform. It's colorless. But the same that ferric can reoxidize or you can leave it to the air, it comes back. So you can make TiO2 in ethanol and just put methylene blue, shine light, dig acid, it will become colorless, right? But you open it, the thing, and leave it to air, the dye color comes back. Because it's reduced and it's reoxidized back to the dye. It didn't degrade completely. That's a very, we use for demonstration, this one. TiO2 colloids, if you make it, throw some dyes. If it is reduced, it will come back. If it is reversible.
So on slide number 45, you have shown something relationship between zeta potential and the slide number 45. The increase in zeta potential allows electrophoretic deposition.
Yeah, see what
So how you
happens
can
is
correlate
cesium,
that?
it's very interesting. When you make cesium-lead bromide, cadmium sulfide, for example, you can electrophoretically deposit. But we never succeeded in depositing cesium-lead bromide alone because it doesn't have charge for some reason, very low charge. Okay, so that's why when you apply field, it doesn't go. But when you put a cadmium sulfide layer, that increase in zeta potential, it became more negative, right? Then in the electric field, we could deposit this film. So that's why, because we could deposit, but this one alone didn't do it. So this is another confirmation that we had a different surface compared to your cesium-lead bromide.
Thank you, sir.
Anybody else?
Yes. Dear delegate, we have more questions that on the day personally exact. So for lunch today, it takes around 1 hour, and if you are asking students, because of that, we interact. Thank you.
Ladies and gentlemen, following
Good afternoon. And we have been talking about electrocatalysis. Okay. This talk is going to be different. Okay. So this is trying to tell you, if when you are doing experiments, sometimes you see what you want, right? And then you make a fits in everything, but don't check other possibilities. And I will give you 10 different types of mistakes that one can encounter when doing electrocatalysis and photocatalysis. And I want to just highlight that the examples I've given here is not to criticize somebody or trying to tell their work is bad, but how sometimes a small ignorance of trying to find the problems gets into the literature, and then people like me come here and tell you that this is wrong, right? So when I say this is wrong, I have to be 100% sure, right? I have to give you proof that why this is wrong. And the reason I'm giving you, because I don't want you to repeat the same mistakes what these guys did, okay? So that's the one. We published one virtual issue. There are, again, this is a nice article if you want to do. It's a collection of editorial articles people have written. It is not uncommon for researchers to draw an important conclusion based on a single finding without carrying out control experiments or checking possible artifacts. Sometimes it is an artifact, sometimes it is just wrong conclusion. Performance claims, even inadvertently, can quickly result in becoming a target of criticism. So you don't want to be getting to that one. And here is a thing, correlation versus causation. The bird is sitting here, right? The question is, did that bend because of the bird sitting there? It's an observation is right? But you need to find out the reason behind it. Just because what you see is not right. Again, you can stop me from any time in the between, okay? So, number one, reaction vessel and other experimental conditions, right? People always use it. So if you are using alkaline solutions, the glass can dissolve, especially when you keep it for a long time. So this is an article, again, it is not my article, okay? The majority are somebody else's article. They have pointed out that effect of dissolved glassware on the structure sensitive part of the copper 1 voltammogram KOH. Because most of sometimes CO2 reduction, people do it. But now the glass this is the fresh KOH and a day old KOH. You start seeing it. Again, this is in PFA coated. You know, the PFA is like a Teflon. Not much difference. And here you see between glass freshly made and after 1 day, the changes. So again, in addition to these ones, sometimes you have got impurities in the glass. 1 day the synthesis works great because you had some impurities. Other day it will not work because you cleaned up the glassware. So sometimes using glassware and cleaning is very important, even for things like cyclic voltammetry. Again, this is done by Peter Sebastian, who is an Indian science. A lot of people do CO2 photocatalysis, right? And they do a lot of inorganic solvents. And they shine light. Sometimes they use entire xenon lamp because that's when they start seeing the products. But what is important is to check just the blank with nothing, just the solvent and shine the light. What kind of products they are getting? So he has done a series of, they have done it. This is, again, rate of product formation. Okay, different products, carbon monoxide, methane, ethane, hydrogen. Okay, this is lots and lots of paper come up. So here he is using acetonitrile, TOA, triethanolamine, this some carbonate, and ethyl acetate. These are common solvents people use, right? And then again the scale goes up here. You can see here some of them like TOA and TEA have large formation of hydrogen, for example. And again, it varies This is as CO2 catalyst. This is a visible light. Even with visible light, you can do it. This is full arc lamp, xenon lamp. The UV plus visible. This is visible light only. This is under full arc. And this is under visible light. So again, you can see here various products are formed during this one, and they made a table here to show you which solvent one should be using for the experiment. Like if you are using, you better watch out. If you are visible, these are no-nos. They can give you products. Whereas acetonitrile is okay if you are using visible light. But if you are using UV, you can see here, you can get products out of it. So again, it is cautioning how it is. The second one, right? Medium pH dictates reaction mechanism. You use certain pH. Do you know there are how many schemes people use alkaline medium and give you this reaction? If you go to alkaline medium, there are no H plus ions. If your pH is 10, your H plus concentration is 10 to the minus 4. pH is 12, pH 12 is 10 to the minus 12, right? So it tells you how low concentration of H plus, and they cannot get reduced. So if you are using alkaline, this is wrong. Okay. Again, acetyl reaction mechanism. If you are using sulfide, the moment you add water, you can dissolve sulfur dioxide in the water, right? And then you measure pH. It's always pH 11, 12. Why? Because it grabs a proton from this water and forms SH minus instantly. That is, and leaves you OH minus, that's why you get pH 12. So recognize the fact that when you have S2 minus, it doesn't stay there. This is what the species is. Again, at pH, what likely at pH? There is another article written by this one, pH matters when reducing CO2. Because you get different CO2. When you CO2 dissolve, you have got CO3 2 minus in alkaline medium, HCO3 minus, and H2CO3. It's carbonic acid, if it is there. So you need to know what species you are trying to reduce. Again, there is another one. This one is preparing alkaline electrolytes for electrochemical applications. Again, in alkaline electrolyzers and other things, they use very high concentrations. Such as standardization must consider the presence of other species. Inaccurate alkali concentration can lead to erroneous pH estimation. Impurities. And here they are giving an example of nickel hydroxide and OH. It forms NiOH, right? So again, how it affects the transitions based on the pH. This is during the charge, and this is the peak shift they are seeing because of the this NiOH formation. Maybe it needs a battery. Maybe it needs a battery. No, it was fine. Okay, got it. Activation of, while subsequent charging results in NiOH. As I said, you may be starting with nickel hydroxide, but you are forming changing. So you need to know the conditions with which these things happen. Okay, this is probably one of the most encountered things, the role of sacrificial donors, right? As I mentioned in the morning, photocatalysis has two parts. If you want to have your stable photocatalyst, You need to consider both reduction and oxidation. Okay? And then you can do is charge separation doing it. You may be looking in hydrogen production. You may be looking into CO2 reduction. And typically people write sacrificial donor products. What are the products? Tell me what are the products. Just don't write products, right? So, and then there is another thing. And this is known as, in the 80s, called current doubling effect. Whenever they are seeing current, and if you have like photoelectrochemistry, you add in ethanol or methanol, your current doubles. And the reason is the oxidized alcohol, in this case methanol becoming a methoxy radical, it's an electron donor. So it can give an electron back. And you can see more yield of it. That's another process other than doing it. Again, there is another article that is written here. Okay, so we wrote into tell us the complete story, right? So just when you have oxidation, tell us what happens to the oxidation. This is the final reaction for methanol oxidation. For every methanol molecule, you can expect 3 hydrogen molecules. So here it is CH3OH. You can first it is 1 electron, and then eventually you get this product. So if you are using this one, you are getting hydrogen from reduction as well as oxidation. I briefly mentioned it earlier, but this needs to be taken into account. To summarize, radical reactions in photocatalysis play an important role in determining the photo distribution. One should not make claims on focusing on single process. Important to consider all possibilities. Okay? New researchers interested in research should refer to earlier literature. There is a lot of literature explaining these things. Here is an example, right? Perfect photon to hydrogen conversion efficiency. They claim that we report a record 100% photon to hydrogen production efficiency under visible light illumination, water splitting half reaction. This result was accomplished by utilization of nanoparticle-based CDSC rods with hydroxyl anion radical, right? Number one, you go into the data, see it. They're using pH 14, 15, 16. Can someone tell me how to make pH 16 medium? I don't know. Can you make pH 16? Okay, you see how much sodium hydroxide you have to dissolve to get that one, right? Even this could be 10 molar, if everything dissociates. This should be 100 molar, right? But anyway, so they did it in alkaline medium, right? See the mechanism here. Is this the right one in alkaline pH? It's a published paper. It probably has got a lot of citations. A lot of news reports saying that they made a major breakthrough of getting 100% efficiency. And then they use isopropyl alcohol 10% by volume. As I mentioned earlier, this can also give you alcohol oxidation hydrogen. They didn't account for it, right? So that is the one. If you think 100%, this one is more than 100%. Right? And what did they use? Sodium sulfide. But they gave an explanation that it is a MEG, multiple exciton generation, because it went from in this region a little bit higher. But they didn't do this reaction, right? That gives you, and there are oxidation of SH minus yields hydrogen. So again, these are all famous journals, okay? So don't get me wrong. But it slips through and gets published, and person like me, especially as I get older, you get more grumpier, right? You try to complain, the older people. Okay, so I'm just telling you that just watch out for this one. Just don't believe just because it is said more than 100% give an explanation. Dig into the data, see what could have gone wrong. Put into all the tests. If it passes, great, that's a great work. If it fails, then don't worry about spending time reading it. Here is another example of oxalate by a binuclear copper complex. I think I showed you this example. And they published first in Nature Communications. Then they retracted it. And the retraction said during the follow-up article, the main claim, namely CO2 was reduced from oxalate, is incorrect. Rather, the detected oxalate is formed by the oxidation of ascorbate in the system. So they retracted the paper. And then they wrote the third papers, what is the real mechanism to doing it? So first you publish a wrong paper, you retract it, and then you correct it again. So Nature Communication got 3 times the money. Okay, there is another editorial by I think Bannerman which explains undesired role of sacrificial reagents, right? People have been publishing this, take care of it, but people still continue to use it, ignoring all these things which is there, and this is a mechanism. And he says usually most experimentalists are not even interested in these processes because all that they measure is the formation of hydrogen. As elaborated above, hydrogen will be formed through both direct reductive as well as indirect oxidative paths. Okay, so again, like in the case of the organic donors, any qualitative or even interpretation of the respective results will therefore be highly speculative. Okay, now you complained about it, how do you probe it, right? I showed you, I think, this one in the morning. So we made this film in a bipolar membrane. So we made CDS on this cation exchange side by exchanging cadmium ions, and then we deposited metal on this side. Again, we can put gold, platinum, palladium, whatever you want on the other side to make this one. And then we put it in our H cell. So this one now really separates out the oxidation part and reduction part, right? Same particles. So if you separate out the two and we shine the light, and we can measure how much hydrogen is coming here, how much hydrogen is here. And sure enough, when you try to measure, we see this ascorbic acid and sodium sulfide, TOA, CH3OH. That's why these are most popular ones, okay? Sodium sulfide. All cadmium sulfide people use sodium sulfide because they see much higher yield with that one. The only thing it doesn't do is sodium sulfite because it doesn't have H in it. Okay, that's number 3. What is number 4? Establish the reaction mechanism, eliminate alternate possibilities, right? So again, I talked about graphene oxide earlier. People have used in photocatalysis quite a bit, right? So lots and lots of papers. In fact, we started it very early on. We observed it. We also did the photocatalysis, right? But can graphene oxide survive photocatalysis? Okay, so you can see here, we published this paper, and this was our last work using graphene photocatalysis. After that, we didn't use it. Because again, the questions came in, if TiO2 can oxidize organics, because graphene oxide is also inorganic, right? It's all bonds. So basically, you put TiO2 and your RGO and oxidize it, okay? And you get these fragments, and then ultimately it forms carbon dioxide. So this is, I showed earlier, when you oxidize it, this orange color, this is reduced color, right? So what you do is, you take a graphene oxide solution. I want you to try it. Go back and try it if you are working with graphene oxide photocatalysis. Add some TiO2 powder or whatever suspension you are using. Right. Hold it before the UV lamp to excite TiO2. Again, we use UV light, okay? In 30 minutes, it became this, almost same color, like an oxidized graphene. In 60 minutes, yellowish. Later on, it becomes totally clear water. So that means my support material is not very stable. And this is a simple experiment to check, right? We should have checked it long time back. It took us several years to check this one and wrote it. And there have been reports, for example, if you put in a TEM and bring an electron beam, wherever there is a metal sites, it starts to make a hole. We have also published a called Making Graphene Holy. If you generate hydroxyl radical, for example, if you put hydrogen peroxide and you shine UV light, it forms OH radicals. And if you have a metal particles, wherever there is a metal particle, it sort of acts to generate hydroxyl radical and you make holes. And this particle moves to some other side and makes holes. And again, you can see here, you can TM image and ultimately it becomes water. Now look at the papers here, right? This is ultra-fast, efficient transport of hot plasmonic electrons. See how many buzzwords are here, right? Ultra-fast, efficient, hot, plasmonic, and highly efficient, visible light responsive photocatalyst. Now, what they are saying is they are putting this gold catalyst on this RGO surface. And they see these products compared to carbon dioxide reduction only when they have RGO and gold nanoparticles. If there is no gold nanoparticles, nothing. Only when there is a gold nanoparticles and this one, they see the products, right? That's how they concluded it. And they say that this electron, they tunnel through this one and reduce it. It's a very complicated mechanism. It's not a simple mechanism. So they never thought their products may be coming from the metals oxidizing the products. And that's what it is. The metals can oxidize and give you the same products. There is another one. CO2 hydrocarbon fuels by CO nanoparticle decarbon oxide. They could have just tried without CO2, right? There is no data, CO2. And again, they use other ones, they don't. Again, this one also came in Angawante Chemi very recently. Again, the titles are more fancier than actual result, okay? Simultaneous harvesting multiple hot holes. Multiple holes or multiple electrons to extract from any particle is extremely difficult. And so far, nobody has proved or showed that you can extract electrons or holes more than one. It's always one at a time. Even CO2 reduction, you may be the product is a multiple electron reduction, but when the electron goes, it's first from CO2 minus dot, then the second electron or two CO2 minus come and give you oxalate ions. So the reaction occurs on the surface, but it is never 4 or 6 electrons at a time. So again, here what they did was they used these gold particles and they studied this benzyl alcohol oxidation, okay? And what did they use? They used this one as an oxidizing agent. All peroxides are oxidizing agent, right? So only thing they saw was when they shine the light, it went up. Whatever that product, the conversion they were looking. That benzyl alcohol getting converted to some products. And it was very responsive to the gold. One of the things is gold particles, as I said earlier, they can peroxide, it can generate hydroxyl radicals, right? Number two, gold particles, when you heat it, it heats up. When you heat up, you're catalyzing your hydroxyl radical reaction. So this is nothing to do with these multiple hot holes. They are so short-lived, it's very difficult to extract. Lot of these plasmonics have make-believe things because there is some other effect is taking over. And this is a classic example. It's a thermal effect. And look at that, it drops down. Why it is dropped down? And when light off, it is still going up. I don't know. So this is the one that, so again, now the question to ask, did authors exclude thermal effects? No. Is it whole transfer or hydroxyl radical in desorption? They didn't discuss this, right? Can one extract multiple hot holes? Any evidence in the literature? No. But it gets published, right? Because they put these fancy titles, the reviewer never questioned it, it got published. See, even in the dark, there is a conversion. Okay, so that's about this one. And now, photocatalytic process may alter the surface chemistry. So if you have, like, again, it's a nice article. It is well known that metal sulfides are thermodynamically less stable than metal oxides under oxidizing potentials, and metal nitrides and phosphides are less stable than sulfides, and so forth. Again, these ones, what happens is they're used, and under OER condition, you get a shell around it. And this could be metal oxide or hydroxide. Like in the nickel oxide, if you start with a nickel compound, you can get nickel oxide, nickel oxyhydroxide. So it's very important to test your thing after you do the reaction. Okay? Do the evaluation parameters reflect intrinsic activity of electrocatalysts in waters? Again, this is again written by an Indian scientist from IIT, I forgot the name. Again, what they did was loading, right? Whenever people compare, my catalyst is better than your catalyst, right? So you always compare in performance. But there are a lot of parameters when you compare. There is loading, how much catalyst you loaded on the surface of an electrode. What is the surface area? In the electrocatalysis, they should be calculating electrochemically activated surface area. So all this parameter comes, you cannot just say my catalyst is better than yours, right? So that's what it is. And then they were trying to always, in this one, they measure Teffel's law and the potential with which, and that's what they have plotted here, splitting. To avoid errors that occur with the Teffel's law, we also suggest the use of polarization curves that are normalized with this electrochemically determined surface area rather than the geometrical surface area. Know the limitations of measuring this over voltage at 10 milliamps and the Teffel's slope because the loading matters. And another one is do not ignore reactions at the counter electrode. Okay. So again, this is very important. What happens is when you have two electrodes, right? You have working electrode and a counter electrode and a reference electrode. And most of the time you apply a bias so that you are controlling the potential of the working electrode. So if your working electrode says plus 0.5 volt, your counter electrode could be minus 0.8 or 1 volt, minus 1 volt, because they are passing the current just to maintain that 0.5, because there is a lot of resistance losses along the way. So it is not controlled. So when you are using, say, reduction of CO2 or some other hydrogen, you are applying a negative bias to this working electrode, and your platinum electrode can get oxidized and generate platinum ions. And these platinum ions can diffuse in and can deposit back on your working electrode. So coupled with reduced graphene oxide was prepared, which exhibits almost hydrogen evolution reaction. Most of these people, they claim, I made a non-noble metal electrode and it behaves exactly like metal electrode. right? So here it is. There are couple carbide reduced graphene oxide catalysts for efficient hydrogen production. Then this is another one, synthesized from, was also reported to show similar HER performance as that of PT. And look at the citations, right? Very good citations. However, by carefully studying this published work, it was noticed that PT was unexceptionally chosen as a counter electrode without applying an ion exchange membrane across the working and counter electrode during the measurements. So somebody else commented on it, saying that what happens is when you have this bias, when you maintain negative, this one dissolves and creates platinum ions. And this can diffuse in and can deposit. Yes, you started with your non-noble metal catalyst, but the platinum oxidized dissolved. And they did the work. If you look in the paper, they did without membrane and with membrane, and they showed it. If you add a membrane in here, that blocks. It will not pass through, so you will not get deposition. So this is another one. The presence of, chloride, if you use it, it forms a complex and comes out. PT should not be selected as a counter electrode for measuring the activity of HER unless it is coupled with an ion exchange membrane, which was commonly ignored. That is the drawback in this one. So you can read this article for more detail. Yeah?
So what are the other options? Because we don't have ion exchange membranes, those things, etc.
No, again, you have to use some kind of a barrier, right? Otherwise, don't use platinum. This one, I don't know. You have to use some other one that will not oxidize. Graphite is okay. But this is a real fact, okay? And they have done it. It's not just they commented it. They have done the experiments with and without membrane and show you the difference. You evaluate electrocatalysts and decomposition products. Sometimes when you have these electrocatalysts or a photocatalyst, they can decompose. Okay, so here is the example. Especially there is a lot of interest in nitrogen reduction, right? And people use these nitrides. Mononitrides of zirconium, niobium, chromium, and a DFT guide. So somebody did theory and said, okay, these are the great catalysts for nitrogen reduction. And someone reads it and goes and tries it. Electrochemical N2 fixation to ammonia under the ambient conditions, right? At highly efficient and selective catalysts. So they use this molybdenum nitride. And here is it. Critical assessment of the catalytic activity of vanadium and neodymium nitrides towards dinitrogen reduction. And comprehensive testing of the materials under a wide range of conditions and ambiguously demonstrates that inability to catalyze the electrosynthesis of ammonia from dinitrogen, as well as the propensity of vanadium nitride and this niobium nitride to release lattice nitride in a non-catalytic process, which gives NH3 under reductive condition. So essentially, this one decomposes. There is no catalysis, but this non-catalytic way. And most of the time, the ammonia people measure is so small, it can come from anything. So that's why it is. It is an article, electrochemical dinitrogen reduction to ammonia, catalysis or decomposition. So again, I'm saying that some of these are published works in good journals, right? But somebody else takes it apart. So contamination effects. Again, in ammonia reduction is much more. So it also happens in CO2 reductions. The amount produced ammonia is usually as low as a nanomole level, not even micromoles, right? Therefore, it is challenging to accurately measure and unequivocally attribute to the electrochemical N2 fixation, especially with the interference of various contamination. Two types of contamination sources. One out is ammonia or NOx present in the air, human breath, and rubber gloves. That's a possible contamination. Intrasystem contamination. Nitrogen containing compounds in the feed gas, electrocatalyst membrane, difficult to probe independently. So again, nitrate, nitrites, they are much easy to reduce than nitrogen, so they may contribute this one. So again, you can take a look at this one. Here it is, somebody wrote how to do it right. Photocatalytic CO2 reduction, identification, elimination of false positive result. How to eliminate. So they made a sort of a workflow chart. And this one, focusing on the base materials, should be extremely cautious when they exclude the false positive results from carbon contamination. And here, confirm purity in regard to the carbon-based molecules. And then you can do the photocatalytic test, and then you can report. And if it is not, then a shared labware, gas, reactor, right? Somebody else might have used for something else. So all these things, you have to take it, things. And here is another one, paper, right? Engineering electro and carbon materials for CO2 reduction. If you see here, they are using carbon dots, source of carbon, right? And they are showing the reduction here, process that gets in. But where is the oxidation? They never looked into it, right? Could it be the source? I don't know. You be the judge. Can carbon dots get oxidized just like graphene? Here is another paper. It was published in PNAS. Solar photothermochemical alkane reverse combustion. It's basically CO2 reduction. Okay. They are using CO2 to form CO and other things. And they use this TiO2 photocatalyst in this reactor here, and they reduced and they claimed it. Right? Nice paper, they showed everything, everybody believed it. But to give credit to them, if you identify there is a problem in your paper, if you retract it, it's okay. Because there was genuine mistake made, and that's what they did. In a retraction notice, we have now demonstrated our results are largely due to artifacts, and the underlying thesis of this work has not been shown. Okay. So another one is the cell design. Know the electrochemical parameters. So this is a nice Nature review article, and they are given various different types of cell configurations. If you want to do electrocatalysis, what could be the cell designs and how to minimize some of the problems for the gas phase and also liquid phase reactions. So again, it's the H-type cell and configuration. If you want to do some in situ studies, you can use a internal reflection like cadmium selenide crystal with the FTIR. So the probe pulse comes in, bounces back near the electrode surface, and you can do the chemistry. Or you can do other ways of X-ray absorption. So there are a lot of people are now trying to do in situ measurements. So you can have electrochemistry and do these measurements to do this. Another most important thing is the IR compensation, right? In electrochemistry, when you apply voltage, you just set whether doing it. But this guy went ahead and did IR compensation, reporting of electrode potentials are critical for the CO2 reduction. And he found out 63% of the published papers have no record of IR compensation. Okay? That means you may be applying -1 volt, it may be actually -0.5 volt. So that is the one. Then there is a post correction. People later on measure it and then say what the voltage should be. Partial compensation, full compensation, and current interrupt. So again, the range in the product distribution could arise from the different ways the potential is measured and reported in the literature. And they are saying these are the products, right? For the same reaction, people see different ratios. And that ratio may be coming from the lack of IR compensation. Another major thing, 2 electrode versus 3 electrode measurements. Know the difference. In a 2 electrode measurements, when you do it, your counter electrode itself is a reference electrode. Okay? So this one is okay, but you should know that that's a reference electrode. But most of the people, when they apply bias, they use a reference electrode. Okay? And the reason they use reference, who is going to tell me how the reference electrode works or why it works? Anyone? You all have used it, most of it, right? Anyone? Okay, one of the things, the potential of an electrode is governed by Nernstian equation, right? So you have an oxidized form and a reduced form. If you take any other things, it typically is very difficult to maintain the concentration at the electrode surface. So these early electrochemists, they were so smart, they came out with an idea. We will use sparingly soluble salts, like calomel, we call it Hg2Cl2, right? AgCl, right? So if you write the equilibrium AgCl giving you Ag plus and Cl minus, right? That is very, very low. So it likes to be in AgCl. It's a sparingly soluble, we call it. The constant could be of the order of 10 raised to 20, 30, it's very little. So as a result, your chloride concentration at the electrode surface is constant. Because of that, its potential doesn't change. Same way with the calomel electrode. The potential doesn't change because there is this one. So typically, you have to use a bridge, not just stick in a wire. So you have to separate so that it always maintains chloride concentration. In calomel electrode, Hg2Cl2, Hg and KCl. Either there is a saturated calomel or 1 molar KCl they use. So that the chloride concentration is constant. So as a result, the Hg2 plus becomes mostly Hg2Cl2. As a result, calomel electrode has minus 0.241 volts, right? That's a constant voltage. That's why it is called reference, right? So if you use just PT, like in the morning, saying it will do for that particular experiment, but it is not fully controlled. If you just use a metal electrode, you will be able to do the experiment, but it can vary during your experiment a little bit. So that's why they use this sparingly soluble thing and they add it. And what it does is it measures the resistance between these two. That's how the IR compensation. And it tries to compensate so that there is no voltage drop between this electrode and the reference electrode. So once you do that, then you're done. But this electrode is never controlled. So in order to maintain the potential here, they have to pass a higher current so that it is that potential. That's what the potential stat controls the potential. So that's why here it is not responsive. It is just like a dummy electrode. Anything that happens, you cannot rely. If you want to see it, switch it over to this one and apply potential. Then it is fine. So make this as a working electrode. So this one is, there is some measurements getting the basic right. And one of the things is try not to make claims for hydrogen or anything when you are using 3 electrode assembly. That is not an ideal condition. If you use 2 electrode, yes. And there are a lot of people do it. They will do a correction. They will take for water oxidation 1.23 minus applied voltage. There is the voltage that you required and then divide it by the charge and then calculate efficiency. But ask yourself, is it a realistic? You never know how much power is being pulled out to maintain that potential. It's very hard to find. And I talked about this burden of proof. Over a century ago, the Thomas Chamberlain recommended generation and testing of multiple working hypotheses in a scientific inquiry to guard against drawing premature conditions. Again, scientific hypothesis must be falsifiable or refutable. So in all by means, we should not be able to disprove it. To advance science, we should attempt to discredit rather than prove our preferred mechanistic ideas. And again, I told you that for your experiment, you have to be your own critic. Try to criticize. Try what things can contribute to that observed thing. So this is what you will get it. We must exercise vigilance to avoid make claims that proof exists where it does not. Okay, so that's sort of coming to an end. Relevant control experiments and checking for possible artifacts. That is important part. Multiple working hypotheses should be tested to support the conclusions, and as many research groups are currently working with photocatalysis, it is important to have a checklist to validate important findings. Okay? Okay. Okay, there is a new controversy. Have you been following this? This guy called Diaz, Ranga Diaz, right? He is in University of Rochester as assistant professor. He published a paper in Nature, right, on a superconductivity. Quickly pointed out mistakes, his collaborators, it got retraction, right? So the paper got retracted. Then he continued his study, and then he published another paper earlier this year. This is also heavily criticized. Now all the co-authors except him have wrote to the Nature, please withdraw this paper. We don't want to be part of this. And his thesis, people have checked it. He has plagiarized his thesis, copied from other places. Okay? So for a short time, there was a lot of publicity, but this is what happens when it is. It doesn't matter whether you're publishing Nature or any journal. They do get scrutinized, and this is what happens. And probably he will lose his job, because his thesis has been withdrawn. Okay, questions? Was it useful? Any questions? Any thoughts? Or did you got scared away? Doing right thing is not a problem, okay? You have to have some patience, ask questions, do it right. It's only when you're in a hurry and you don't have time to go through all the data, the students present it, and you write it, because it's our job to train the students and put them in the right path. We discuss in our group with students mainly because I don't want them to do the mistakes. So discuss these things with your group, researchers, and students in a journal club. Just ask questions in a published paper. Everybody's quiet. I think I scared them away. There is one more. Let's see whether. 1 second, okay. It's not here. No, this one. No, in the box if I go. What? Just 1 minute, I'll see whether. Okay. 1 minute. I will show you something else. I got one more. This will be useful.
After this lecture, can we go to chemist and relax 5 minutes?
Sure. Let's see now. Which one is this? Which one? Academic honesty and up to hold it. So, and changing times and changing practices, sharing knowledge and research ethics. Okay, so let's skip this one. How do you learn ethics from mentor, advisor, fellow graduate students, family, all these things, right? So you learn from different people what to do. Like, first thing is when you are growing up as a kid, your parents will tell you, okay, this is not the right way to do it. You cannot take away things without asking somebody. So these kind of ethics we learn over the way. So every thing we establish. There is nothing like hard written rule, but it's something like our peers or everything doing it. And if you read it, it says 3 sets of obligations of a researchers to adhere to professional standards. Okay? The first one is an obligation to honor the trust that their colleagues place in them. Okay? So when you are working, your group members or your other colleagues, they trust you, right? When you say, I'm giving you a sample, you are giving a really prepared sample. They trust you. Obligation to themselves. Irresponsible conduct in research can make it impossible to achieve a goal. Okay? And this is probably, to me, the most one. Whenever you come to do research, since from your kindergarten until now, think about how much hours and hours you have spent time to come to this level, right? Now don't screw it up, okay? There are a lot of things are easier, things are harder. Just because it's easier, don't go out of the way and do mistake. So that is sort of a thing. That's why you have to get obligation to yourself. And obligation in an act way to serve the public. Because if you go, the publics, they are thinking that you guys are doing great research, right? Whether you are solving energy or solving health problem. I cannot go tomorrow and announce that, well, I discovered a drug that can cure all cancers, right? They will cover the news. It will be all over the news. And it happens all the time. You see it. Some people just want that publicity, just like that Ranga Diaz. He went and said, I made the superconductor, right? All the New York Times, everybody had this big thing that there's a major discovery happened. But that's not the way to distress. So these are the 3. Please remember that your obligation to the place where you are working, obligation to your colleagues, obligation to yourself, and obligation to the public. Again, authorship, right? So again, the list of authors establishes accountability as well as credit. When you have authors in research journal that state person should be listed as the author of a paper only if that person made a direct and substantial intellectual contribution to the design of research. Okay, otherwise add them in the acknowledgement. Including honorary guest and gift authors' duties dilutes the. Now people are putting authors for sale. There are people on the Facebook. They are coming from India, right? They will have a paper that is almost ready to submit, and now people are exposing them. And they're writing back to the some journal saying that, well, this was posted. after publication, because they will not tell you which journal it is. They will say it's impact factor 3.2 journal. So once it publishes, they keep track of it and they inform it. So that is another thing going. Okay, demise of a lone author. So most of it is now joint authors. Author responsibilities. Follow general rules. Ensure work is new and original. Aware of submission. Agree that manuscript can be examined. Provide copies and proper affiliation. Okay, research ethics. So who owns the data, right? So whenever you are working, like I'm working at Notre Dame, I don't own the data. If I leave, everything stays with the university. It is their property, right? Even if I file a patent, they have to approve it, or they say, okay, I'm not interested in it. So you do not own the intellectual rights, your institution does. Okay, this is one of the old case. This guy from Dow Agro, he worked for it and went back to China and he wrote a review article. And Dow, they charged him, and the court decided that yes, he published sort of unpublished data that Dow owns. And I think he was, I don't know, he's going to jail, or at least he paid the fine, this one. So these things do happen, especially if you work in an industry, they're very sensitive to what you take and what you publish. This is from, there is a, in US we call Office of Research Integrity, or ORI. So they are the final authority for any ethics case that comes in. People pressurize. It doesn't happen much other one, but medical communities, people do a lot of manipulations just to get things across because they're doing it. Again, research misconduct means fabrication, falsification, and plagiarism in proposing, performing, or reviewing research. Okay, and that's the definition of fabrication, is making up data. When you don't have something, or a lot of times you see in the TM image, people duplicate same particles or something like that, and that's something. Falsification is manipulating the research materials, equipment, or processes, right? So again, plagiarism is appropriation of another person's ideas, results, words. You can copy figures from other published work, okay? As long as you give the credit to that person, get the copyright permission, give the credit, no problem. If you have to use some paragraph from something, put it in the quote and give the citation where it is coming. Once you put it in it is understood that it is not your words. Even one sentence when you are writing and copying from other works, put it in. If you like that one, is to highlight. It does not include honest error or differences. Just like I showed you that PNA's paper, they retracted it because it was a mistake. That is not a misconduct. Because if mistake happened, they realized. Yeah.
What exactly constitutes an honest error? The definition is not very clear, right?
Honest in the sense that they know we do a mistake, right? I'm not a perfect person. I might have done a mistake. But when it comes to my knowledge that I have done a mistake, most of the time people do send a correction, right? Addition and corrections in the journal, right? That was an honest mistake. For example, if you have a figure, you had a wrong data, and then you realize, oh, this is not the one I wanted to put in, and you have to correct. That is an honest mistake. So you didn't do it deliberately to cheat, right? So that's the difference. And you can see the difference whenever someone does it. It happens to everybody. Honest mistake. There is nothing like perfect. But the fact that we admit that mistake happened and we try to correct it. And there is one way is to write addition and corrections, or in the case, the whole conclusions are wrong, then it has to be withdrawn. Okay? So that's what most people, even Nobel laureates, they have retracted papers. Okay, what is data manipulation and fabrication? Okay, researchers who manipulate their data trustworthiness. Remember that obligation I talked about, right? Here, again, arise from poor experimental design or careless measurements as well as improper manipulation. when a mistake appears in a journal article or book, it should be corrected in a note or editions correction. Okay? So if there is a mistake. For example, this is a manipulation. I don't know how many people remember this. So they published called Chopsticks Nanorods, tuning the angle between pairs with high yield. And this was a guy from Utah, okay? And you can see here, they got chopsticks, nanorods, right? They wanted to see chopstick. If you see it, look carefully, they cut and paste, right? So there was a lot of on social media, people complain, what an idiot he is. He didn't know even how to copy and paste. He left these marks. Okay, other types of ethical voice. There are a lot of these ones, okay? Failure to inform the editor-related paper that the author is under consideration in press. Sometimes people send two, three journals and say which one is getting a thing, and then they withdraw it. And when you withdraw it, right away people know there is some problem, right? Unrevealed conflict of interest that could affect the interpretation of unethical practice involves substantial reproduction of another study, bringing no novelty to scientific community without proper acknowledgement. If such duplicates have different authors, then they may be guilty of plagiarism. Okay. So this is another duplication, right? So this was I handled a long time back, and it got a paper they published, and then later on somebody complained that, well, this XRD is from a different paper, right? So they made this material, I need an XRD, okay, take it, put it. I need a TM image, just rotate it 90 degrees, put it, right? So these are the things do happen. Again, suspected duplicates in the biomedical literature is going up. Sooner or later, ethical violation get exposed. Some famous examples. There was a guy, I think people forgot about him. He's called Henry Schoen. And this article wrote him that he might get a Nobel Prize, right? It was a molecular electronics at the time. And the only problem is he published like 8-10 papers in Nature Science journals in a year, collaborated with a lot of leading scientists, and the problem is he used the same set of data to publish different papers, different molecules. Eventually someone finds it, right? So they did it, and it was a big thing for him. And he was working for Bell Labs, they fired him. He went back, and I think he became a car salesman or something. There is a book written on him. We wish to, again, there are a lot of retractions. Maybe lead author, own institution recommends report to be read. Sometimes institutions step in. So anytime when somebody complains to ORI, the Office of Research Integrity, they ask their university to investigate first and send them the report. And the university hires first the faculty committee, and they look into it. And if there is a case, then they transmit to the ORI, and then they give the final verdict what happened on that one. This is a very funny case, okay? This is one of the university called University of Miami at Ohio. How this plagiarism thing. So this guy, he was a very disgruntled graduate student or a PhD student. So he failed all the exams, and they kicked him out. Says, you cannot do PhD. So he says, well, if I cannot do PhD, I know what's going on. So he went to the library, pulled out all the theses from everyone, right? And he found out about 35 theses that has, like sometimes all these experimental modeling, introduction, they were all copied from one thesis into the other, right? So he first complained to the university, and they said, well, you are a disgruntled one, we don't care to you. So he went all the way to university. Then he called in the news, and the news media loves it, right? They came and investigated this, yes, and then they say university is doing it. Then the university didn't have any choice but to ask all the 35 people, rewrite their thesis first they have to admit that they plagiarize, rewrite the thesis, and or they will withdraw their thesis, right? So you can see the 35 people, they're all from mechanical engineering. And this is what happens. Sometime you do it now is fine, you will get your degree. But sometime later it might come and haunt you. Just don't do it. Okay? You can write little, it's fine. Write your own. You don't have to be this very big. So that is the one. And in fact, some of them were already having an academic position somewhere. Okay, so again, there are various ways journals and other people detect. Most of the time, somebody else sends out, okay, have you seen this paper that just published, because his author name was not there, right? So this is what the problem is. So again, that's the one. Sudden withdrawal from a publication when it is in process. Again, typically they ban for a few years. Most of the time, if there is any small problem, we just put on a watch list. There are a lot of these ones. You can search for retracted, you will find it. There is a lot of papers. You will see retracted papers. This was very early on. A chemist in India has been found guilty of plagiarizing and falsifying more than 70 papers, wide variety of scientific journals, 2747, according to document from his university. Some journals editors left reeling, and he didn't have any instrument, nothing. So he will just make up and write it, right? This was before the paper mill. Now the computers will write for you. But in this case, he was writing for everyone else. He'll say, I will collaborate and I will write and those things. So this one. So this is another famous case. Again, he was also on the news and everything. He just got out. Paper retracted. Paper from Clark Business. Unaware. And these are the responses, right? When you ask somebody who plagiarized, the first one is, there are probably only X amount of words with Y amount of statements. I have no idea why the pieces are similar. I was not involved in this article. I have no idea why my name is included. This article was mainly done by a young fellow. I made the correction in text, complete the article. Unfortunately, doctor has died. So we can't ask him for the reason. I am not a native English speaker, so I do have problem in expressing ideas. You and other English language speakers are lucky from this point of view. To be honest with you, I was not aware of the fact that I need to take prior permission of the authors. The last one is interesting. The corresponding author has been my teacher and a very good one at that, from whom I have learned many things. My respect him was utmost level until I found that he had been plagiarizing papers from all over the world. Okay. It's not a big moral deal, but again, there is another article here. Again, a lot of times, music, for example, right? People copy it. Some professions, they let you do it. So depending upon the profession, there are different rules for plagiarism. So one need to understand what is allowed, what is not. It's like in social media, nothing is copyrighted. Everything copy something, you see a video, you send it. In this world, they are protected. So respect other authors when you are doing and those kind of a thing. So again, according to this one. That's it. Thank you. I thought I'll just share some thoughts with you. So any thoughts, anything, any experience? Yeah.
Sometimes you draw the graphical abstract, right?
Yeah.
So that we see someone's image and keeping that in PowerPoint page, just change the colors and the design. So there we need to cite the...
Yeah, if you are doing it, it says it's modified. Something you say it is modified from this guy or whatever. If you use somebody, give the credit too, right? Suppose just turn it around. If someone uses your figure without giving credit to you, how do you feel? Right? So that's exactly, you just reverse the role and then you will understand why we have to give credit.
Second note I had regarding cross-reference. Sometimes if I get some idea, right?
Yeah.
I cite from some paper.
Yeah.
But it will again have a cross citation from some other source. And it will have from some other.
Yeah, right. But theoretically, you are supposed to go to the original one. Like, if you want, again, I told you, like in photocatalysis, you had this lot of older people, right? If you want to say some radical reactions, give them the credit. Although they are dead, they deserve it, right?
So, but for example, the first interpretation and this so all need to be cited, or like how is it?
Again, depends upon the situation, right? If you really need both sides to tell how it is grown, you use it, all the citations. But if it is just for a passing comment, you can recite a review article and say, go and read all the papers cited therein.
So then one thing about plagiarism, for example, plagiarism or anything like retraction. So how is that the responsibility shared by authors? I mean,
Everyone gets the shares. The moment your name is in a paper, there may be 20 authors. You are supposed to read and verify everything what is there. You cannot say, oh, this figure was done by somebody else. I'm not involved in it, right? But the blame comes to everyone. But
now, like most of the people, they do collaborative research, right? So some part of the work is done by some group and some. So in that sense, it becomes difficult for every expert to get into the other aspects.
But at least you have to read, right? If you then disagree, you have to make that thing happen. For example, that Ranga Dia's case, he has like a lot of collaborators. They all went with him. Henry Schoen, they all went with him, all collaborators. Why didn't they check in? Because they were happy that they were getting paper in Nature, right? So now they say when everything is exposed, we don't want to be part of it.
Some of the journals now, they are asking for individual contribution. Like
Yeah, but you can always make it up. You can always make it up. But theoretically, anytime, for example, my name is in anybody's paper, it is my responsibility to read and understand and make sure everything is right. And that's why it's very important whom do you collaborate with. There are a lot of times, I don't disagree, I said, put my name in the acknowledgement. I don't want to be part of it. Although I helped you certain things, I don't want my name in the paper because they wanted to publish in a rush or whatever it is without checking. It's fine, they can go ahead and do it, right?
Sir, I have one question. How to cite the data taken from government websites and other websites?
How do you correct?
Government websites or any other website.
Oh, you put URL, right? You can put URL and when did you access it. The problem with the URL is they can change any day, right? So today it is there and tomorrow it may not be there. But at least when you say until that date, it was valid. So you have checked that it is there. And there are places where they copy and keep all the old URLs too.
Some research papers cite author name, but in government websites, no any author or no anything paper to.
So if you are citing URL, there is no need to
Author.
mention the authors.
Yeah.
There is no need.
But research paper मध्ये बघितलेलं की त्यामध्ये आहे author.
नसतं बा.
It's okay, it's a minor thing.
Sir, my question is regarding the plagiarism allowed percentage in India as per the UGC is it 10%. Below 10% is plagiarism allowed. This criteria is all over the. What is the criteria?
It's not that they say, nobody can say 10% of plagiarism is allowed, okay? What they say is the similarity. 10% in similarity, because sometimes some of the phrases are very common, right? The experiment has been carried out. We observed something. So there are some common statements people use, and these are not plagiarized. It is just a common. But when they check for plagiarism check, these sentences, they get marked, right? So in journals, we ignore those things. What we are looking in journal is if your entire paragraph is picked up, then it is a problem. Just few phrases, nobody is going to say that. So don't use that word 10%, 15%. It is just that similarity index, they call it. That something looks similar to the earlier published work. Again, there are lots of these phrases. Your methods, experimentals, all these things, we employed hot injection method to prepare semiconductor nanocluster. Probably it is a very common sentence, right? There's nothing wrong with it. The problem is when you copy the entire text, a paragraph or a page. Yeah.
Sir, I wanted to ask about the predatory journal. There's a Bell's list, predatory journals.
Yeah.
So there is a famous Bell's list in which they regularly they update the journals which seem to be predatory. So how much do you have confidence in that list? What are the red flags if we are deciding for journalism?
Okay, I think the last part you said it. How do you red flag a journal? Because the open access policy has corrupted a lot of these people, right? So tomorrow you can start a journal, make a nice web page and say, in India, you can publish for 500 rupees paper. There are a lot of sites, right? So, and they will publish anything. And people have done it like they send their children's report. Send it to them, they will publish it. Give them 500 rupees, they will publish it. Okay? So they just to get them even, they have done it. It's going to continue. And the problem is, why do you want to consider those journals, right? Number one, because these are not indexed by Web of Science or Scopus. So that is the first test for any journal if you want to publish is, are they indexed in Web of Science and Scopus? Sometimes these guys falsely claim that they are being indexed, okay? They will also give an impact factor. It's totally, because it's a false journal, right? They can write anything they want. So first to check is, you go back and put the journal name, whether it exists. If it doesn't exist, don't proceed. If it is indexed and you still have doubt, right? You can check with a librarian. Can you please check with me? Okay? And you can also see who are the editors and who are in the editorial boards. That sort of tells you, like, I get so many invitations to be on the editorial board. I say, no, I don't know this journal. I don't want to be part of something I don't know, right? So these guys, they want to bring in the credible thing and doing it. So there are a lot of this. Now, another thing is happening is the scientific meetings. These are pre-read meetings. Every day I get 2 to 3 invitations, okay? And I block them. I don't know, they appear. Global Summit in Paris, okay? Or they're fancy places. They do it. What they do is they will just hotel doing it, and they want to collect registration fees. And they will get a hotel room, there will be 5 people, and you go and present and go home, right? And they collected the registration fee, $1,000. So that is also started. So always see who is inviting you, whether that person has a credibility that is there. And the other thing you may want to do is phone check. Is anybody else, who else is publishing in this journal, right? That also tells you how credible it is. So that is one thing. And recently there was it came in Science about a month back. This guy, I think somebody, and he signed up for webinars, right? So basically you Zoom your talk in, and he made them sign an agreement that they will pay $2,000 for presenting their talk. And the bottom, he said, this is for your photo permission to give. And the people signed it. They forgot to read that fine line that he's supposed to pay. And when they asked it, says, no, I'm just giving a webinar. Why should I pay? No, there is a registration fee you have to pay. And now he's charging up to something like $80,000 with fines and all these things. And it is in the court now. The people have gone into the court asking. So in the Sweden, it's going to be sometime decided soon. Who is right? Is they have to pay it 80,000 or this guy is broke? So there are a lot of crooks like this. So just watch out. So it's unfortunate. It's unfortunate. These are like really predatory. So you don't have to refer to the predatory list. You just follow these guidelines.
Sir, one more question I had. For example, like when we talk about the copyright and those all stuffs, right? So when we use Sci-Hub, there is some sort of moral or ethical dilemma because we are...
One thing about Sci-Hub, again, for everybody, it's great that they give you free papers to read, but there is no free lunch, okay?
Right.
So when you log in, they have access to your computer and your institution's computer. So through you, they are getting access to the institution computer. And they can hack anything you want in the thing. So they have all of that, their interest.
So like if you talk about middle income and low income countries where affordability of paper is very difficult.
You write to the author, whatever paper you want, you send me an email, I will send you a PDF file of my papers. That's the old style. In the old style, we used to send a reprint card. We see a paper, we write, could you please send me a reprint? And another 8 days later, the reprint came in. So you text and do it. Just send one email to that author. See whether it comes in a day. Your library can get you interlibrary loan. All papers. But you want to see it right away. That's the problem. This will take one extra day. All authors will be happy. Suppose if I write to you and say, send me a copy of paper, will you be happy to send you?
Yeah.
Yeah. But somehow that practice has forgotten. So anybody from this side?
Yeah, you have okay, somewhat more time today. You can take again 5 to 10 minutes more.
So, but where is the tea?
Yeah, already he's outside.
He is on the way.
I have been talking.
I have a question.
Yeah.
Suppose we are doing some experimental work and we know that certain parameters we have to cross check. But we do not have suppose some financial backup. And suppose we are a PhD student, so we are like in a hurry to publish the paper. So that is the situation. So
I gave you the example, so you decide which path to take. Yeah.
Last question, I have a doubt.
Yeah.
When we respond to review, so multiple times we write the thank you so much River for your valuable.
You don't need to thank them. Don't worry.
Yeah, multiple
No,
times.
that is just an habit.
Yeah.
You think that, yeah.
What is the simplest way to respond to review?
Just don't say, you don't need to thank you. If it is really, I use it when they really find a mistake that I omitted, like, something mistake in a figure, right? Some axis was not right or it doesn't come, sometimes conversion problem. Okay, thank you for pointing it out this, but not for every comment. Don't do that. You don't need it. And another thing for any reviewer comment, if you believe the reviewer is wrong, don't agree with everything. You can rebut it. You can refuse it. A lot of times you say, this is beyond the scope of the study. Because they want to do 10 different things. Just tell them, this is beyond the scope of the study and we will follow it up in the next study. because there is a limit how much you can do in one study. So, which is fine. The editors don't think that they go and check mark everything, do it. Whether how much, are there any major concerns that you addressed? Like sometimes somebody asking you to do the control experiment, right? Suppose you're shining light with your catalyst. Somebody asks, have you done without a catalyst? Right? That is a genuine comment. So he might check that, and then if he didn't do it, he might send you back again. Yeah, go ahead. According to the yeah.
So we find about the journal finder is there, the software.
Okay.
We ask about the title and abstract. We have to put into that. Then they suggest like it will suit for this step. So will it be the same?
I don't know. What I'm saying is, it's not hard, right? Most of the time, we know which journals we read, right? And those are the journals you want to publish, isn't it? Pick those journals and send it to them. So you don't need journal finder. Typically, I ask students, where do you want to send it? These are the possibilities, right? So finding out the right journal is important. It's true. Like if you have physical chemistry, there are several physical chemistry journals and chemical physics, right? Journal of Chemical Physics, Physical Chemistry, PCCP, ChemPhysChem. So those are Langmuir. Those are standard journal in physical chemistry. If you are in materials, there is so many journals in materials, right? Chemistry of materials, nature materials. You have got Royal Society has a materials journal. Or if it's applied, you can got applied materials journals. So you can pick based on typically what you read. The best thing is you cite the references, right? So that is the best gauge for you. You don't need a journal finder. Go and see which journals you have cited. Those is the most appropriate. No. So the cited references will tell you which is the most appropriate journal.
Hello, sir.
Yeah.
My article is already published by Image Journal.
Yeah.
And sometimes Lambert or Taylor Francis publications are asking to me write a chapter on that title. So can I write a chapter?
Yeah, you can write a chapter. No problem. But I don't know who is going to read it.
Okay.
Because they will read your paper. Because chapter book means they have to pay money, right?
Sir, it's my general question.
Yeah.
How you fit at the age of 71? Because it's not possible for researcher.
What?
How you fit at the age of 71?
How do I?
You fit your body, fitness. What is the formula?
Of your fitness.
The most.
It's a very inspiring story.
Yeah.
Last more than 40 years he is running 4 miles with 6 kilometers per day. In a week.
Not every day. In a winter time, I slow down.
No. Sir, that's true. Because and one more thing, out of 7 days in a week, at least 1 or 2 days he is finishing 10 kilometers.
No, yes.
Though he's one of the unique identities that he is hardcore researcher. You are reflecting how he is delivering, how what about his research work and everything. Everything he is discussing in a lucid manner. But one more important thing is he is a hardcore athlete also. Last he came here on Sunday, Monday morning. Today is Wednesday. Tomorrow, of course, they start at around 5:30, 6 o'clock, and around 6:20 we are on the ground of the Shivaji University. Almost I ran with him. He is a really hardcore athlete.
No,
if you are going to see the I am running marathon. Many also delegates may run that. Might be running marathon. You might be knowing the pacer. What is the role of pacer? Or who will be the pacer? the pacer who already proved itself or himself as I completed, let us see, 21 within 1 hour, 10 minutes or 2 hours. So such those who already finish different marathons of 21 kilometers, 42 kilometers, they of course they will be the pacer. The second important role of the pacer is that who is supporting to all the athletes who are participating in a particular marathon. Okay, yeah, during running now, pacer is telling that no, you are doing well, you are running great, your speed is great. And of course, student friends or delegates, I am happy to inform that this course is happening because of the consent, though he is given the consent in 2017-18, but in 2017-18 onwards we are waiting to him, and in 18-19 because of time constraint of Professor P.V. Kamath, followed by the COVID situation, we didn't conduct that one. But of course, a few months back, we received the email from again the IIT Kolhapur. So already your course has been approved for this GIAN program. And if the foreign expert having the permission or having the consent to come in India in offline mode, of course we can conduct. And this course is happening because of only the presence of Professor P.V. Kamath. So big give us big applause. So of course, along with that, if I don't know about the other facts. If other facts with Professor Kamath's view, then please inform to our delegate.
Okay.
How you are the fit at the age of 70, 71. If you are going to see such a personality, he is only what we call age is just number. Yes.
Okay. First of all, thank you for having me and giving the opportunity to talk to you. Okay. As I mentioned, our generation came out. When I was in studying, there was no electricity. We were studying with the lamps. Again, many students maybe are still having problem, but that's how we started, right? We didn't have TV, no radio. So only thing, and we don't have any private tuitions. That is the biggest blessings for me, right? So as soon as you come, you throw your thing and you go and play it. It got dark, come home, wash your thing, do homework. That's it, right? So no, forget it, computers, phones, nothing. So, but that also made you more creative because we didn't have much toys at that time. So we have to make our own. Whoever had the bat, he had the king. So he made all the rules to play the game, right? So that thing happened. So for all of you, again, as you mentioned, it's a marathon. Yes, the career is a marathon, right? He also said that you need to practice. That's what I say. Keep some kind of a schedule or discipline every day to do certain things. And then the rest of the things. And at least half an hour to 45 minutes, please devote on yourself. Okay? Same thing, when I go running, it is on me. The rest of the time, I do it for all others, right? A lot of times people say, I'm busy, I got this. It doesn't matter. It's in the night, morning, whatever fits your schedule, use that one. And it is very important. If you don't have to run, you can just go for a walk. That is good enough. Your mind will relax. And don't use the headphones in your ear. Just walk. Because the nature sounds are beautiful. Whether it's a peacock, I know it is a little not that pleasant, but the beautiful birds or something singing. So you get that freshness. So try to do those things and have a discipline. And there is no substitute for hard work. So that is my thing, right? I'm not growing up, I'm not a gold ranker or thing. But I was average or above average, whatever it is. But I always had this one to do certain things. So don't give up something, you set a goal and pursue it. There are more opportunities than what I was having, and so try to capture it. You don't have to be like somebody else. Be on your own. And also yesterday mentioned, believe in yourself. Forget about the other world. Don't do things because what someone might think what they will say. Whatever you think is right, and do it. So again, it's a long journey. In that long journey, you meet so many people. They influence you. Even today, from youngsters like you, I learn. When I talk to you, when you ask questions, I learn from you. Okay? You may be asking a question because you may not know, but that is sort of an eye-opener for me. What I should be telling next time somebody else. So it is always a two-way street. It is not that I know everything. I don't know. I've learned a lot from my students. So you have to keep that mind open so that doing it. Once you gets into your head that I am the supreme, there are a lot of people, scientists like that. You cannot talk. But that for them, nobody goes near them. Nobody talks to them. So because I'm friendly, you will come and talk to me, right? So I can learn from you. So that is one of the things you have to do it. Again, there are a lot of things you can do. But again, I really want to thank Professor Dalekar and everyone else who is involved for giving me the opportunity. I know it's hard. The reason is it takes 3 days or 4 days, coming and going, right? It is strenuous. So I started on Friday, came Saturday night to Bangalore, and then Sunday morning here. And now again, my return journey will be the same thing. So that sort of is the main factor for trying to see the window when you can visit. So most of December times are more convenient because everything slows down. But from January until May, summer is a little more, but summer is bad here to come. Otherwise, summer is okay. So again, we hope to see you succeed. And if you have any questions, always write to me. I always respond to email. It will not be a long email. Mine is always short. So,
Thank you. One more request to all of you that tomorrow early morning we have session of course PV Kamath sir, and as per the schedule we are going to start that one at 10 o'clock, but sir wants to leave this place around 11 o'clock. So instead of 10 o'clock we are going to start that session 9 o'clock.
We can start 9:30.
Yeah, 9 o'clock would be okay.
Yeah, we'll finish early.
Yeah. So 9 to 10:30 he is going to deliver everything, and immediately he wants to leave this place around 10:45 or 11 o'clock. Yeah. And one more thing, yesterday he also requested to all of you that if you have any idea,
if you want to discuss tomorrow, bring it in.
Tomorrow, you have this chance to discuss. Just within a couple of minutes, 2 to 3 minutes. In that the time you want to discuss the idea, it will be considered as a brainstorming session, no doubt. So along with his talk on the challenges and opportunity in energy technologies, along with that you have some times reserved for the brainstorming, because
I'm going to present my today's first talk.
Yeah, it's okay. Because if you are going to see the statement of Eleanor Roosevelt, so small minds discusses the people, the average minds discuss the event, and the great minds like Professor PV Kamath discusses the ideas. So tomorrow you have the best this session. You may have the chance. If you have the idea, you discuss with Professor Kamath. Okay, thank you, sir. So with this, you enjoy the tea. Thank you so much. Bye bye. And one more, may I invite Professor DM Kore sir. He handled this whole day as a chairman. So may I request Dr. S.N. Taide sir, please felicitate Professor DM Kore sir by offering shawl, then a memento and a book. Yeah. I want to complete the overall formality. Yeah. Suraj, take the photo. Thank you so much. So 8:30 to 9 o'clock tomorrow, okay, you will have the breakfast. 9 o'clock onwards, okay, we are going to start the session. Thank you so much.